Langchain experimental RL chain base embed list type. Detailed definition of the variable. Detailed definition of the variable goes here. Components. Component 1. The embed list type parameter in langchain experimental RL chain base controls the embedding strategy for a list of text inputs. For example, in a question answering system, the embed list type could determine how the context documents are transformed into embeddings for efficient retrieval and comparison against the user's query. Component 2. It specifies how the embeddings are generated and processed for efficient and effective interaction with the RL model. Different embed list type options can leverage techniques like batch embedding for faster processing or use specialized embeddings for specific tasks, such as sentiment analysis or translation. Architecture of the variable. Description of the architecture supporting the variable. The architecture of the RL chain allows for flexible embedding strategies by offering various embed list type options. Each option employs a different approach to handle the embedding process, ensuring optimal performance for specific use cases. For instance, one option could use a pre-trained language model to generate embeddings for each input, while another might involve creating embeddings based on the frequency of words in the input list. Role of the variable. Explanation of the variable's role in the system. The embed list type parameter plays a crucial role in determining how text inputs are transformed into embeddings for use within the RL chain. It enables efficient interaction between the RL model and the text data by defining the embedding strategy. Imagine a chatbot trained to provide customer support. The embed list type parameter could be used to determine how the chatbot's knowledge base, which might contain a large corpus of support articles, is converted into embeddings for efficient matching with customer queries. Advantages of the variable. It allows for efficient handling of large lists of text inputs, optimizing the embedding process for faster and more effective RL training. For example, in a large-scale image captioning model, the embed list type parameter can ensure that a massive dataset of image descriptions is processed efficiently, leading to quicker training times and better model performance. It provides flexibility in choosing the most suitable embedding strategy based on the specific needs of the task and the nature of the text data. Consider a sentiment analysis task where you need to analyze a collection of customer reviews. Depending on the language and complexity of the reviews, you might choose a specific embed list type that effectively captures the sentiment expressed in the text. Challenges of the variable. Ensuring that the chosen embed list type aligns with the specific requirements of the RL model and the task at hand is critical for optimal performance. For instance, choosing a highly efficient embedding strategy for a complex language generation task might lead to a loss of nuance and result in less coherent outputs. Balancing the computational efficiency of different embedding strategies with the need for accurate and meaningful embeddings can be challenging. For example, using a very simple embedding method might lead to faster processing but might not capture the subtle semantic relationships between words, potentially impacting the overall performance of the RL model. Langchain experimental smartllm base smartllm chain summary. None. This class provides a foundational structure within LangChain's experimental smart large language model LLM module. It's designed to simplify the development of intelligent chains, which utilize LLMs for various tasks. This class offers a streamlined approach to building chains that leverage the capabilities of LLMs. Component 1. This class acts as a foundational element within LangChain's experimental smart large language model (LLM) module. Its purpose is to simplify the creation of intelligent chains, which utilize LLMs for various tasks. The class offers a standardized framework for building chains that leverage the power of LLMs, making the development process more efficient and user-friendly. Component 2. This class offers a framework for constructing chains that interact with LLMs, manage state, and execute actions. It allows developers to create chains that can engage with LLMs, maintain their internal state throughout interactions, and perform specific actions. Imagine a chain that interacts with a knowledge base via an application programming interface API, retrieves information, and then summarizes it using an LLM. This class would provide the structure and mechanisms for this chain to manage its state during each step of this process. This class acts as a foundation for crafting chains that leverage LLMs, offering flexibility in chain composition, state management, and the execution of actions. This class provides a flexible structure for creating chains that utilize LLMs, allowing developers to design chains that can adapt to various situations and manage their internal state. It also allows for the integration of different components within the chain, like custom functions or external services. This class facilitates the creation of chains that utilize LLMs in a structured manner, offering a foundation for various tasks. This class provides a structured framework for building chains that leverage the power of LLMs. It simplifies the process of creating chains that utilize LLMs for specific tasks, such as summarization, question answering, and code generation. By providing a foundation for building these chains, it allows developers to focus on the specific logic and actions required for their specific use cases. Simplifies chain development by providing a standardized framework. This class simplifies the development of chains by providing a standardized framework, reducing the need for developers to write repetitive code and allowing them to focus on the core logic of their chains. This standardization promotes consistency and reusability across different chains, enables the creation of more sophisticated and robust chains. This class allows for the creation of more sophisticated and robust chains by providing the necessary tools for managing state, interacting with external services, and leveraging the power of LLMs. Developers can build chains that can handle more complex tasks and adapt to changing conditions. Requires careful consideration of the chain's architecture and interactions with the LLM. This class requires careful consideration of the chain's architecture and interactions with the LLM, as the design of the chain directly impacts its performance and effectiveness. Understanding the capabilities and limitations of the chosen LLM is crucial for building a successful chain. Requires proficiency in LangChain and LLMs to effectively utilize this class. This class requires a certain level of proficiency in LangChain and LLMs to effectively utilize it. Understanding the concepts and principles behind LangChain and LLMs is necessary for designing and building chains that leverage their power. Langchainexperimental, RL chain, based on none. This class represents a single step in a reinforcement learning chain, including the prompt to be used for the language model and the reward function to be used to evaluate the language model's response. For example, consider a chain that takes an input of a question and outputs an answer. One step in this chain could be to generate a prompt that asks the language model to provide an answer to the question, and another step could be to evaluate the quality of the language model's response by comparing it to the correct answer. Component 1. A template string that can be used to generate prompts for the language model. This template can include placeholders for variables that will be filled in at runtime. For example, a prompt template could be "Please provide a concise answer to the following question." This template could then be used to generate prompts for different questions, such as "Please provide a concise answer to the following question: What is the capital of France?" Component 2. A function that takes the language model's response as input and returns a numerical reward value. This reward value is used to evaluate the quality of the language model's response. For example, a reward function could be used to give a higher reward to responses that are more accurate, more relevant, or more informative. This class is a building block for reinforcement learning chains. A chain can be constructed by combining multiple based-on objects, each of which represents a step in the overall process. For example, a chain could be constructed from a sequence of steps that first generate a prompt, then provide the prompt to the language model, then evaluate the language model's response, and then take an action based on the evaluation. This class encapsulates the logic for a single step in a reinforcement learning chain, including the prompt to be used for the language model and the reward function to be used to evaluate the language model's response. For example, this class could be used to define the logic for a step that generates a prompt to ask the language model to provide a summary of a given document, or a step that evaluates the quality of the language model's response by comparing it to a reference summary. Advantage 1. Allows for the creation of complex chains by combining simple building blocks. For example, a chain could be constructed from a sequence of steps that first generate a prompt, then provide the prompt to the language model, then evaluate the language model's response, and then take an action based on the evaluation. Advantage 2. Allows for the use of different prompt templates and reward functions for different steps in a chain. For example, a chain could be constructed from a sequence of steps that use different prompt templates to generate different types of prompts, such as prompts that ask the language model to provide a summary of a document, a translation of a text, or a code snippet. Challenge 1. Designing effective reward functions can be challenging, as they need to accurately reflect the desired outcome of the chain. For example, it can be difficult to design a reward function that accurately reflects the desired outcome of a chain that is designed to generate creative text formats, such as poems or stories. Challenge 2. Creating prompts that lead to desirable responses from the language model can be difficult. For example, it can be difficult to create a prompt that will lead the language model to generate a response that is both creative and informative. Langchainexperimental, smartllm, base, smartllm chain. A YAML representation of the smartllm chain object, which describes its definition, components, architecture, role, advantages, and challenges. A chain that manages interactions between a user and a smart LLM. This chain acts as a mediator, facilitating conversations between a user and a sophisticated language model known as a smart LLM. The smart LLM chain orchestrates the exchange of information and ensures a smooth interaction between the two entities. Component 1. A user-provided language model LLM. Usually an instance of a chat OpenAI. This component represents the user's choice of a specific LLM. Often a powerful language model like chat OpenAI. It acts as the primary tool for processing natural language and generating responses. Component 2. A smart LLM. Used to interact with the user-provided LLM. This component refers to a sophisticated and intelligent language model, designed to manage and optimize the interaction between the user and the user-provided LLM. The smart LLM plays a critical role in guiding the conversation, ensuring efficiency, and achieving specific goals. The chain consists of a smart LLM and a user-provided LLM interacting in a loop. The smart LLM receives user inputs and sends them to the user-provided LLM, getting back responses and then using them to make decisions. The smart LLM chain operates in a continuous loop, where the smart LLM receives inputs from the user, passes them on to the user-provided LLM for processing, receives the generated responses, and then uses them to make informed decisions about the next steps in the interaction. This iterative process ensures a dynamic and goal-oriented conversation, enables users to interact with a smart LLM, which then orchestrates interactions with the user-provided LLM to achieve a specific goal. The smart LLM chain empowers users to interact with a highly intelligent smart LLM. The chain acts as a bridge, enabling users to utilize the capabilities of the smart LLM by managing the communication with the user-provided LLM. The goal is to achieve a specific objective through this collaborative interaction. Allows for flexible interaction with a smart LLM, while leveraging the capabilities of a user-provided LLM. The smart LLM chain offers flexibility in interacting with a smart LLM. This flexibility allows users to customize the conversation and leverage the specific strengths of the user-provided LLM. By combining the capabilities of both models, users can achieve a more diverse and powerful interaction. Enables intelligent management of the user-provided LLM, ensuring efficient and effective use. The smart LLM chain facilitates the intelligent management of the user-provided LLM. This ensures that the LLM is used efficiently and effectively, maximizing its potential and delivering optimal results. The smart LLM optimizes the interaction by making informed decisions about how to utilize the LLM's capabilities. Smart LLMs are still in development and may not be perfect. Smart LLMs are a relatively new field of artificial intelligence (AI) and are constantly being developed and improved. While they offer significant potential, they are still under development and may have limitations or imperfections. This means that the smart LLM chain may encounter situations where the smart LLM's responses or actions are not ideal or perfect. Potential for errors in communication between smart LLM and user-provided LLM. Since the smart LLM chain relies on communication between two separate language models, there is a potential for errors or misinterpretations in the exchange of information. This could lead to unexpected outcomes or miscommunication, highlighting the importance of robust error handling and communication protocols within the chain. Langchain-experimental RL chain-based parselines. Description of the parselines method in langchain-experimental RL chain-base. The parselines method within the langchain-experimental RL chain-base module serves the crucial role of parsing text input provided to the reinforcement learning RL chain. It transforms the input into a format suitable for processing by the RL chain's components. Components of the parselines method in langchain-experimental RL chain-base. Component 1 of the parselines method in langchain-experimental RL chain-base. The parselines method is an essential component of the RL chain because it acts as the initial step in the transformation of raw text input into a format usable by the chain's components. It is like taking a raw ingredient and preparing it for cooking. Component 2 of the parselines method in langchain experimental RL chain base. Typically, the parselines method begins by splitting the input text into individual lines. This could involve tasks such as tokenization or extraction of specific information. A real-world example might be reading a recipe and extracting the ingredients and instructions. Architecture of the parselines method in langchain experimental RL chain base. The architecture of the RL chain usually involves a sequence of components, with parselines often being the first step in this sequence. Imagine a chain of assembly line workers, with the parselines method being the first worker to receive and process the raw material. Role of the parselines method in langchain experimental RL chain base. The parselines method plays a vital role in the initial preprocessing of text input for RL chains. Its primary purpose is to structure the input into a format that facilitates further processing by subsequent components, just like you would organize your tools before starting a construction project. Parselines prepares the input for the rest of the chain. Advantages of the parselines method in langchain experimental RL chain base. Advantage 1 of the parselines method in langchain experimental RL chain base. The parselines method efficiently transforms raw text into a structured format that is suitable for processing by the RL chain. It's like organizing a messy room into a functional space. Advantage 2 of the parselines method in langchain experimental RL chain base. This method provides a consistent format for input across various components of the RL chain, ensuring that all components are working with the same data. It's like using a standard blueprint for different builders on a project. Challenges of the parselines method in langchain experimental RL chain base. Challenge 1 of the parselines method in langchain experimental RL chain base. Handling complex input structures, such as nested lists or tables, can be challenging for the parselines method. Imagine trying to read and understand a complicated spreadsheet without a proper guide. Challenge 2 of the parselines method in langchain experimental RL chain base. Optimizing the parselines method for speed and efficiency is crucial for handling large amounts of text data. It's like trying to process a large database quickly and effectively. Langchain experimental.sql, Vector SQL, Vector SQL database chain. A detailed explanation of the Vector SQL database chain, a tool for interacting with SQL databases using natural language. A chain that combines Vector SQL with LangChain to provide a natural language interface for querying SQL databases. This chain allows users to interact with SQL databases using natural language queries, eliminating the need to learn complex SQL syntax. For example, a user could ask what is the average price of products sold in the last month, and the chain would translate that into a corresponding SQL query and execute it against the database, returning the desired results. Component 1. Vector SQL, a tool for executing SQL queries using natural language. Vector SQL uses a combination of natural language processing and machine learning to understand the intent behind a natural language query and convert it into a corresponding SQL query. This allows users to interact with databases in a more intuitive and user-friendly way. Component 2. LangChain, a framework for building and connecting language models with other tools and data sources. LangChain provides the infrastructure to connect Vector SQL to a specific SQL database. This enables the chain to execute the generated SQL query against the database and retrieve the results. It essentially acts as a bridge between Vector SQL and the database. facilitating the entire query execution process. The vector SQL database chain is built upon a chain of components that work together to translate natural language queries into executable SQL statements. It uses a vector SQL model to interpret the query and then uses langchain to connect the model to a SQL database. For example, a user's natural language query like "What is the total revenue for the last quarter?" is first processed by the vector SQL model, which understands the query's intent and translates it into an executable SQL statement. This SQL statement is then passed to langchain, which connects to the database, executes the query, and retrieves the results. The vector SQL database chain acts as an intermediary between users and SQL databases, enabling them to interact with the data using natural language. It allows users to interact with SQL databases without needing to learn or understand complex SQL syntax. This makes accessing and manipulating data easier for a wider range of users, including those who are not familiar with SQL programming. Advantage 1. Easy-to-use users can query data without needing to learn SQL syntax. This makes querying data more accessible for a wider range of users, including those who are not technically proficient in SQL. Users can simply ask questions in natural language, without needing to understand the underlying SQL commands. Advantage 2. Flexible. The chain can be used with different SQL databases and vector SQL models. This flexibility allows users to tailor the chain to their specific needs and environments. For instance, the chain can be used with databases like MySQL, PostgreSQL, or SQLite. Similarly, different vector SQL models can be used based on the specific requirements of the query and nature of the database. Challenge 1. Accuracy. The accuracy of the vector SQL model can affect the results of the query. The accuracy of the vector SQL model is crucial as it directly impacts the quality of the generated SQL queries and the resulting data retrieved from the database. If the model misinterprets the natural language query, the generated SQL statement might be incorrect, leading to inaccurate results. Challenge 2. Security. The chain needs to be configured securely to protect the database. Ensuring the security of the chain is paramount as it involves access to sensitive data stored in the database. Proper security measures should be implemented to prevent unauthorized access to the database and protect the data from malicious attacks. LangchainExperimental SQL vector SQL output parser. Definition. Parses the output of vector SQL's query method. This method is a core component of vector SQL, responsible for retrieving and processing data from a database based on user queries. The output of the query method, which is typically a data frame containing the results, is then analyzed and formatted by vector SQL output parser for user consumption. Components. Component 1. Vector SQL output parser utilizes a SQL query. This query acts as a structured and efficient way to specify the data retrieval process, defining the specific data elements to be extracted from the database. It leverages the power of SQL to perform complex operations such as joins, filtering, and aggregations. Component 2. To extract the relevant information. The vector SQL output parser interprets the results from the SQL query. This involves analyzing the data frame, identifying the required data points, and transforming it into a readily understandable format for users or subsequent analysis. Architecture. Utilizes a SQL query to access and retrieve data from a database. The query defines the criteria for data selection, filtering, and transformation. The output of the query is then processed by vector SQL output parser to extract and format the desired information. Role extracts data from a data frame, which is a tabular data structure commonly used to represent data in rows and columns. It efficiently extracts and organizes data, making it accessible for analysis and visualization. Advantages: reduces the need to manually parse and extract data from raw outputs. It automates the process of extracting and transforming information from a data frame, freeing up time and effort for more valuable tasks. Extracts information easily, providing a streamlined and efficient way to access and utilize the relevant data from a data frame. This makes it easier to work with data, enabling quicker insights and analysis. Challenges: requires the ability to construct effective SQL queries. The accuracy and relevance of the extracted information depend heavily on the quality of the SQL query. May require extensive knowledge of the underlying database structure and schema to effectively craft SQL queries and interpret the extracted data. langchainexperimental.sql, vector SQL, vector SQL retrieve all output parser. A detailed description of vector SQL retrieve all output parser in YAML format, elaborating on each scalar value. A parser that converts the output of vector SQL into a format that can be used by LangChain. This parser acts as a bridge between the results generated by vector SQL and the functionalities offered by LangChain. It ensures that the information extracted from vector SQL is compatible with LangChain structure and functionalities. In simple terms, vector SQL retrieve all output parser makes it possible for LangChain to understand and utilize the information retrieved by vector SQL effectively. Component 1. Vector SQL is a powerful tool for retrieving information from SQL databases by utilizing vector search capabilities. It leverages the power of embedding models to represent data in a vector space, enabling efficient retrieval of relevant information based on similarity. This makes it highly suitable for tasks involving semantic search and retrieval of data that goes beyond simple keyword matching. Component 2. LangChain is a framework designed to streamline the process of building applications that interact with various data sources and languages. It provides a collection of tools and components that simplify the development of complex language-based workflows. LangChain offers functionalities for tasks such as text generation, question answering, summarization, and translation, empowering developers to build sophisticated applications that utilize the power of natural language processing. It uses the vector SQL output to pass the results into a format that can be used by LangChain. Vector SQL retrieve all output parser receives the results from vector SQL, which are often in a format specific to vector SQL's internal operations. It then analyzes and transforms this output into a format that aligns with the requirements of LangChain, enabling seamless integration with LangChain's components and functionalities. It is used to parse the results of vector SQL retrieval queries. Vector SQL retrieve all output parser acts as a translator between the outputs generated by vector SQL retrieval queries and the components within LangChain. By standardizing the format of the vector SQL results, it ensures that LangChain can effectively process and utilize the retrieved data. Advantage 1. Provides a consistent format for vector SQL results. This ensures that all results from vector SQL are presented in a uniform structure. making it easier to process and understand the information retrieved by vector SQL. This consistency significantly simplifies the integration of vector SQL with other components within a LangChain application. Advantage 2. Makes it easier to use vector SQL results with other LangChain components. The standardized output format facilitated by vector SQL retrieve all output parser ensures seamless integration with other LangChain components, allowing for diverse applications and workflows. For instance, you could use the output of vector SQL, parsed by vector SQL retrieve all output parser, as input for a LangChain-based chatbot or a text summarization application. Challenge 1. It may not be able to handle all possible vector SQL output formats. Vector SQL allows for diverse output configurations and formats based on specific use cases. It is possible that vector SQL retrieve all output parser might not be equipped to handle all variations in vector SQL's output, requiring further development to address these variations. Challenge 2. It is not yet well documented. While vector SQL retrieve all output parser offers significant advantages in integrating vector SQL with LangChain, its functionality and usage are not yet fully documented. This lack of comprehensive documentation can make it challenging for developers to understand and utilize the parser effectively. Langchainexperimental SQL vector SQL output parser. Definition. Detailed definition of the variable goes here. Components. Component 1. A class that parses the output of a SQL query and converts it into a format suitable for vector database indexing. For example, this class can take a SQL query that retrieves customer data from a database and transform the output into a list of dictionaries, where each dictionary represents a customer with fields like name, address, and purchase history. Component 2. This class uses a SQL database connection, query, and output format to retrieve data from the database and transform it into a list of dictionaries. This class can connect to a PostgreSQL database, execute a query to retrieve information about products, and then convert the result into a list of dictionaries, where each dictionary represents a product with fields like name, description, and price. Architecture. Description of the architecture supporting the variable. The architecture supports parsing SQL query output for vector database. Indexing. The class takes SQL connection details, query, and output format, retrieves data from the database, transforms it into a list of dictionaries, and then stores the dictionaries into vector database. For example, the class can connect to a MySQL database, execute a query to retrieve product reviews, transform the output into a list of dictionaries, and then store these dictionaries in a vector database. For efficient semantic search. Role. Explanation of the variable's role in the system. The class plays a crucial role in bridging the gap between structured data in SQL databases and vector databases, enabling powerful search and analysis capabilities on structured data. This class allows users to leverage the power of vector search on structured data, enabling them to perform complex queries like finding similar products based on customer reviews or identifying customers with similar buying habits. Advantages. Provides a consistent and structured way to extract data from SQL databases for vector database. Indexing. For example, this class can extract data from an Oracle database about customer demographics and transform it into a format suitable for storing in a vector database, allowing for efficient similarity search based on customer profiles. Facilitates the seamless integration of SQL data into a vector database, enabling powerful semantic search capabilities. For instance, this class can connect to a SQL Server database, extract data about articles from a news website, transform it into a format suitable for vector database indexing, and enable users to search for relevant articles based on semantic similarity. Challenges. The class relies on the presence of a valid SQL database connection and query. If the connection details are incorrect or the query is invalid, the class will not be able to retrieve data from the database. Handling complex SQL queries with nested structures or joins may require additional logic for efficient conversion to a suitable format for vector database indexing. For example, if the SQL query involves multiple joins and subqueries, the class might need to implement specialized logic to handle the nested structures and ensure the data is correctly transformed for vector database indexing. Langchain-experimental SQL vector SQL output parser summary. Definition. The vector SQL output parser is a class designed for parsing the output of SQL queries executed against vector databases. Its purpose is to transform the raw results from the database into a structured format that is easily understood and utilized by downstream tasks within an application. This parser leverages the capabilities of vector databases to produce results that are both accurate and relevant to the original query. Components. Component 1. This class is responsible for taking the output from SQL queries performed against vector databases and interpreting its content. Component 2. The vector SQL output parser is designed to restructure the output of SQL queries into a format that is easily consumable by downstream tasks. This means that the data is organized in a way that makes it simple for other parts of an application to use. Architecture. The vector SQL output parser is built with the goal of seamless integration with vector databases. This ensures that data extraction and processing are efficient and effective. This design enables the parser to efficiently interact with various vector database systems, retrieving data and transforming it into usable formats. Role. The vector SQL output parser is an essential component in the process of retrieving and processing data from vector databases. It acts as a bridge between the database and downstream tasks, ensuring that the information is readily accessible and useful. Advantages. Advantage 1. One of the key benefits of the vector SQL output parser is its ability to present SQL query outputs in a structured format. This makes it easier to understand and work with the retrieved data. For example, it could convert a list of tuples into a table with labeled columns, making the information more readily interpretable. Advantage 2. The vector SQL output parser makes data readily consumable by downstream tasks, simplifying their execution. This means that tasks can directly utilize the data provided by the parser without needing to perform additional transformations. For instance, a task could directly process the structured data for analysis or use it to populate a user interface without any additional steps. Challenges. Challenge 1. Dealing with complex data structures and nested objects can present challenges for the vector SQL output parser. It might require specific parsing logic to handle these complexities. For example, if the database returns results that include nested lists or dictionaries, the parser needs to be able to traverse these structures and extract the relevant information. Challenge 2. Ensuring compatibility with various vector database systems and their output formats is another challenge. This requires the vector SQL output parser to be adaptable to the specific ways that different databases structure their SQL query results. The parser needs to be able to handle variations in data types, data structures, and formatting conventions to guarantee its effectiveness across a range of vector databases. langchainexperimental.sql Vector SQL.get result from SQLDB. Definition. Detailed definition of the variable goes here. Components. Component 1. Langchain experimental SQL vector SQL get result from SQLDB is a function in the langchain library that allows you to retrieve data from a SQL database using a vector database. This function takes a SQL query, a vector database, and an optional embedding function as input. It then embeds the query using the embedding function and searches for the most similar vectors in the database. The function then retrieves the relevant data from the database based on the matched vectors. For example, imagine you have a database of customer data and you want to find all customers who are interested in sports. You could use this function to submit a natural language query like find customers who like sports. And the function would return the relevant data from the database. Component 2. The function supports different types of vector databases, including FAISS and OpenEye embeddings. It also allows you to specify the number of results to retrieve and the threshold for similarity. This means you can customize the function to meet your specific needs. Architecture. Description of the architecture supporting the variable. The function leverages a vector database to store and retrieve data based on similarity rather than exact matches. It uses embedding functions to represent data as vectors in a multi-dimensional space. This enables efficient and flexible retrieval of relevant data. For example, instead of searching for an exact match to your query, the function can find similar data points based on the vector representation. This is particularly useful when dealing with natural language queries where the exact words used may not perfectly match the data in the database. Role. Explanation of the variable S role in the system. Langchain experimental SQL vector SQL get result from SQLDB plays a crucial role in enabling semantic querying of SQL databases. By leveraging vector databases, it allows users to retrieve data based on natural language queries rather than requiring them to write complex SQL statements. This makes it easier for users to access information stored in databases. For example, imagine you are a data analyst who needs to access customer data but you are not familiar with SQL. You can use this function to submit a natural language query like show me the customers in California and the function will retrieve the relevant data from the database without you having to write any SQL code. Advantages. Advantage 1. Allows querying SQL databases with natural language. This feature makes it easy for users to access data even if they are not familiar with SQL querying. For example, a user can simply type show me the products with the highest sales instead of writing a complex SQL query. Advantage 2. Retrieves relevant data based on semantic similarity. This feature allows the function to find data that is semantically similar to the query, even if the exact words are not used. For example, a user could query for products related to sports and the function would return not only products explicitly labeled as sports related, but also products that are associated with sports through other attributes, such as brand or customer reviews. Challenges. Challenge 1. requires a vector database to store and retrieve embeddings. Vector databases require specialized infrastructure and maintenance. This can add complexity and cost to the implementation. Challenge 2. Embedding quality can impact the accuracy of retrieved results. The quality of the embeddings used to represent the data can significantly affect the accuracy of the retrieved results. If the embeddings are not of high quality, the function may return irrelevant or inaccurate data. Langchain experimental SQL vector SQL get result from SQLDB. Definition. Detailed definition of the variable goes here. Components. Component 1. Langchain's experimental SQL vector SQL module is a specialized tool designed for retrieving information from relational databases. It leverages vector embedding techniques to bridge the gap between natural language queries and the structured format of SQL. This module aims to empower users with the ability to interact with databases using human-like language, effectively translating natural language queries into executable SQL statements. Component 2. The getResult from SQLDB function serves as the core component of the vector SQL module. It acts as the intermediary between a user's natural language question and the database itself. This function utilizes a pre-trained language model to analyze the user's question, infer the intended query structure, and generate a corresponding SQL statement. This SQL statement is then executed against the provided database, and the results are returned to the user in a readily understandable format. Architecture. Description of the architecture supporting the variable. The architecture of the vector SQL module revolves around a three-tiered structure. The first tier encompasses the user interface, where natural language queries are inputted. The second tier houses the core logic of the vector SQL module, including the natural language processing engine, the SQL query generator, and the database connection handler. The third tier represents the database itself, where the data is stored and queried. Role. Explanation of the variable S role in the system. The role of getResult from SQLDB within the vector SQL module is paramount. It acts as the central hub for query translation and execution. By accepting natural language input, generating executable SQL, and retrieving results from the database, this function facilitates seamless interaction between users and databases, promoting a more intuitive and accessible experience. Advantages. Advantage 1. The use of vector embedding techniques enables the vector SQL module to bridge the gap between natural language and the structured format of SQL. This allows users to perform database queries using simple English sentences instead of needing to write complex SQL statements. For example, a user could ask what is the average age of customers who purchased products in the last month, rather than having to construct the query like select a V gauge from customers where purchase date. DATEADD month. 1. Get date. Advantage 2. The module simplifies database interaction for users who may not be familiar with SQL, enabling them to retrieve data using natural language queries. This is particularly beneficial for individuals who are not technical experts in database management or SQL syntax. For example, a business analyst could easily query the sales database to see the top-selling products by simply asking what are the best-selling products, instead of having to learn the complex SQL query necessary to retrieve this information. Challenges. Challenge 1. The accuracy of the natural language processing engine is crucial for generating valid SQL queries. Challenges arise when dealing with complex queries or ambiguous language, which may require additional context or clarification. For instance, a query like "What are the sales figures for products with high demand?" could be interpreted in different ways depending on the definition of high demand. This ambiguity could lead to incorrect or incomplete SQL queries. Challenge 2. Ensuring the robustness of the SQL query generator is essential to prevent security vulnerabilities or unexpected errors. This involves handling potential malicious input, sanitizing queries, and ensuring compatibility across different database systems. For example, the query generator must be able to handle input that could potentially cause SQL injection attacks, which are vulnerabilities that allow attackers to execute unauthorized commands on the database. Quality of synthetic data can be influenced by the quality of training data and the prompts provided to the language model. The quality of the generated synthetic data is dependent on the quality of the training data used to train the language model and the quality of the prompts provided to the language model. High-quality training data and well-crafted prompts are crucial for generating accurate and realistic synthetic data. Challenge 2. Generating complex relationships and data distributions may require advanced prompt engineering and model tuning. Creating synthetic data that accurately captures complex relationships and data distributions can be challenging and may require advanced prompt engineering and model tuning. Carefully crafting prompts to guide the language model and potentially fine-tuning the model to specific data domains are essential for generating synthetic data with desired characteristics. LangChain experimental SQL vector SQL database chain. Definition: a chain that combines vector SQL with LangChain for SQL query execution. It leverages a vector database to store and retrieve relevant SQL code snippets based on natural language prompts. This enables efficient query execution against a relational database. Components. Component 1. LangChain, an open-source framework that enables developers to build applications powered by large language models by providing tools and components for integrating LLMs into applications. Component 2. Vector SQL, a system that combines the power of vector search with SQL execution. It leverages the capabilities of vector databases to enable users to retrieve and execute relevant SQL code snippets using natural language prompts. Vector SQL uses vector embeddings to represent both SQL queries and natural language prompts, allowing it to efficiently search for relevant SQL code snippets based on the semantic similarity between the prompt and the SQL code. Component 3. Vector database, a database that is designed to store and retrieve vector embeddings. It provides efficient search capabilities for finding similar vectors, making it suitable for applications involving natural language processing, image recognition, and other tasks that rely on vector representations of data. Architecture. The architecture involves a pipeline that connects LangChain, vector SQL, and a vector database. A natural language prompt is provided to LangChain, which then generates a vector representation of the prompt. This vector is used to search for relevant SQL code snippets in the vector database. The retrieved SQL snippets are then executed by vector SQL against the relational database. Role. Vector SQL database chain plays a crucial role in bridging the gap between natural language queries and SQL execution. It simplifies the process of interacting with databases by allowing users to query them using natural language, eliminating the need for users to write complex SQL queries manually. Advantages. Advantage 1. Improved user experience. Users can interact with the database using natural language, enabling them to access and manipulate data without requiring expertise in SQL or database management. Advantage 2. Efficient query execution. Vector search optimizes the process of finding relevant SQL code, making the query execution faster and more efficient compared to traditional methods that rely on keyword-based search or manual SQL query writing. Challenges. Challenge 1. Data quality. The quality of SQL code snippets stored in the vector database significantly impacts the accuracy of query execution. If the SQL code snippets are inaccurate or incomplete, it can lead to incorrect results or errors. Maintaining the quality of the SQL code snippets is crucial for ensuring reliable and accurate query execution. Challenge 2. Vector database scalability. Scaling the vector database to accommodate large datasets and frequent queries can be a challenge, as the size of the dataset and the frequency of queries increase. The vector database needs to be able to handle the increased workload effectively. Scaling a vector database involves considerations such as storage capacity, processing power, and indexing efficiency. langchainexperimental.sql, vector SQL.get result from SQLDB. Definition. This method retrieves results from a SQL database using a provided SQL query and a set of vector embeddings. The method first transforms the input query into a vector representation, then uses the vector database to find similar embeddings. These similar embeddings are then used to filter the SQL database results, effectively enhancing the relevance and accuracy of the returned information. For example, if a user wants to find products that are similar to Nike shoes, this method can utilize a vector database to find other products with similar embeddings, potentially including Adidas shoes, running shoes, or even sportswear. Components. Component 1. Vector database. This is a type of database that stores and retrieves data based on their semantic meaning rather than exact matches. Vector databases often use techniques like embedding to represent data in a multidimensional space. Examples of vector databases include Chroma, Pinecone, and Viviate. These databases are often used in applications requiring semantic similarity search, such as recommendation systems or search engines. Component 2. SQL database. This is a relational database management system that uses structured query language, SQL, for data manipulation and retrieval. Examples of SQL databases include MySQL, PostgreSQL, and SQLite. Architecture. The method takes the SQL query and the vector embeddings as input. It then uses the vector database to retrieve similar embeddings based on the input embeddings. The retrieved embeddings are then transformed into a list of database IDs. These IDs are used to filter the results of the SQL query, resulting in a more accurate and relevant response. Role. This method enhances SQL queries by incorporating semantic similarity search. It allows for more flexible and nuanced queries, going beyond simple keyword matching. For instance, instead of just searching for shoes, the method can understand queries like comfortable walking shoes or stylish running shoes. Advantages. Advantage 1. Improves the accuracy and relevance of SQL query results by considering semantic context. This can help users find more relevant information by matching their queries with the underlying meaning of the data. Advantage 2. Allows for more complex and nuanced queries beyond simple keyword matching. This enables users to express their search intent more precisely. leading to more accurate and personalized results. Challenges. Challenge 1. The effectiveness of this method depends on the quality of the vector embeddings and the similarity search algorithm used. Poor quality embeddings or inadequate similarity search algorithms can lead to inaccurate and irrelevant results. Challenge 2. Ensuring that the SQL database schema and the vector database schema are aligned for proper mapping of embeddings to database records. This requires careful consideration and planning to ensure that the data is correctly represented in both databases and that the relationships between data points are accurately reflected. Langchain experimental, text splitter, semantic chunker. A breakdown of the langchain experimental, text splitter, semantic chunker component and its properties. A text splitter that splits documents into semantically coherent chunks using a language model. A semantic chunker utilizes a language model to break down long documents into smaller, meaningful sections. This approach ensures that each chunk maintains the original context and avoids disrupting the flow of information. For instance, a document about the history of artificial intelligence could be split into chunks that discuss specific eras, key figures, or major breakthroughs. Component 1. A language model LLM. A language model is an integral component of the semantic chunker, responsible for analyzing the text and identifying sentence boundaries that form semantic units. LLMs are trained on massive datasets of text and code, allowing them to understand the nuances of human language and identify meaningful relationships between sentences. Popular LLMs include GPT-3, Lambda, and BERT. Component 2. A text splitter. A text splitter is a fundamental component of the semantic chunker, responsible for dividing the input text into chunks based on the semantic boundaries identified by the language model. Text splitters use various strategies to accomplish this, such as splitting at sentence boundaries, paragraph breaks, or even custom delimiter patterns. The choice of splitting strategy depends on the specific requirements of the application and characteristics of the input text. It uses a language model to identify sentence boundaries that are likely to form semantic units. The semantic chunker leverages the capabilities of a language model to analyze the structure and meaning of the text. By processing the document, the language model identifies sentence boundaries where a new semantic unit likely begins. For example, a sentence ending with a transition phrase like however might indicate the start of a new semantic unit. The language model's ability to understand context and meaning is crucial for identifying these boundaries effectively. It helps break down long documents into smaller, more manageable chunks that can be processed by other language models or tools. The primary function of the semantic chunker is to simplify complex documents by breaking them down into smaller, manageable chunks. This process enables other language models or tools to effectively analyze and process the information. For example, a question answering system could process individual chunks to find relevant information, while a summarization tool could focus on key sentences within each chunk to create a concise summary. Preserves semantic meaning by splitting documents at natural boundaries. The semantic chunker ensures that the split chunks maintain the original meaning and context of the document. By identifying and splitting at natural boundaries, the tool avoids disrupting the flow of information, making each chunk more coherent and easier to understand. This is particularly valuable for applications where preserving the meaning of the text is critical. Produces chunks that are easier to understand and analyze. By breaking down large documents into smaller chunks, the semantic chunker makes it easier to comprehend the information and analyze the content. This is especially useful for tasks like information retrieval, summarization, and question answering, where processing large amounts of text can be challenging. Requires a language model to be available. One of the key challenges associated with the semantic chunker is its reliance on a language model. This requires access to a suitable language model and the computational resources needed to run it. This could limit the applicability of the semantic chunker in situations where access to powerful language models is restricted or unavailable. May be computationally expensive for large documents. Processing large documents can be computationally expensive, especially when using a language model for semantic chunking. The complexity of the language model and the size of the input document can significantly impact the processing time and resource requirements. This may be a challenge for applications with limited computational resources or when processing extremely large datasets. Langchain Experimental Tabular Synthetic Data Summary. NaN. Detailed definition of langchain experimental tabular synthetic data summary. This variable represents a module designed to generate synthetic tabular data. This module facilitates the creation of artificial datasets resembling real-world tabular data. Components. Component 1. A module that provides a way to generate synthetic tabular data. This module acts as the core of the system, offering functionality to produce artificial tabular data. It uses various techniques and algorithms to create realistic datasets. For example, it might employ generative adversarial networks GANs to learn patterns from existing data and generate synthetic data that follows similar distributions. Component 2. A helper function to generate synthetic tabular data using a specified model. This function acts as a facilitator, enabling the use of specific pre-trained models to generate synthetic tabular data. It takes as input a specified model and generates synthetic data based on the model's learned patterns. Description of the architecture supporting the variable. The architecture of langchain experimental tabular synthetic data summary relies on a modular approach, combining components to achieve its functionality. The central module, responsible for generating synthetic data, leverages pre-trained models to mimic real-world data patterns. Explanation of the variable's role in the system. The primary role of langchain experimental tabular synthetic data summary is to provide a mechanism for generating synthetic tabular data using pre-trained models. This capability serves various purposes, such as augmenting existing datasets, creating training data for machine learning models, or testing applications with realistic data. Allows for easy generation of synthetic tabular data. The ease of use is a significant advantage of this module, allowing users to generate synthetic data without extensive programming or data manipulation. Expertise. This simplified process makes it accessible for a wider range of users, even those without advanced data science skills. Provides a way to generate synthetic tabular data using pre-trained models. The ability to leverage pre-trained models is crucial for generating synthetic data that reflects real-world patterns. These pre-trained models have learned from existing datasets, enabling the module to create data that aligns with observed trends and distributions. Requires access to pre-trained models. One challenge associated with using pre-trained models is the requirement for access to these models. This access might involve using existing models from public repositories or training custom models based on specific data requirements. May not be able to generate data that is representative of real-world data. While leveraging pre-trained models helps generate realistic data, it's crucial to acknowledge that the generated data might not perfectly represent real-world data. The models might capture only certain aspects of the data and may not account for all complexities and nuances present in real-world scenarios. Langchain-experimental, RL-chain, base, prepare inputs for AutoEMD. Description of prepare inputs for AutoEMD. This method prepares the inputs for the AutoEMD function. It iterates over the list of prompts and retrieves the relevant information from each prompt. This information includes the prompt text, the prompt type, and any additional prompt-specific data. The method then constructs a dictionary containing all the collected information, which is later used by the AutoEMD function. Components of prepare inputs for AutoEMD. Component 1. LangChain, experimental, RL-chain, base, prepare inputs for AutoEMD is a method that is part of LangChain's reinforcement learning chain. It's responsible for taking a list of prompts and formatting them to be compatible with the AutoEMD function. Component 2. LangChain, embeddings, base. Embeddings represents the core of the embedding functionality in LangChain. The embeddings object takes textual data as input and transforms it into numerical representations, vectors that capture the meaning and relationships between words. Architecture of prepare inputs for AutoEMD. The method receives a list of prompts as input and returns a dictionary containing the prepared inputs for the AutoEMD function. The preparation process involves iterating over each prompt and extracting the relevant information, such as prompt text, type, and any additional prompt-specific data. The extracted information is then organized into a dictionary, which is used by the AutoEMD function. Role of prepare inputs for AutoEMD. The method plays a crucial role in preparing the inputs for the AutoEMD function, which is responsible for embedding the prompts into a vector space. By collecting and organizing the relevant information from each prompt, the method ensures that the AutoEMD function receives the necessary data to accurately represent the prompts as vectors. Advantages of prepare inputs for AutoEMD. Advantage 1. Simplifies the process of preparing inputs for the AutoEMD function. By handling the formatting and extraction of information from prompts, the method allows developers to focus on the core logic of their application. Advantage 2. Ensures that the AutoEMD function receives the correct data for each prompt. This is crucial for accurate embedding, as incorrect or incomplete data can lead to poor representation and performance. Challenges of prepare inputs for AutoEMD. Challenge 1. The method may need to be adapted for different prompt formats and structures. This is because prompts can come in various forms, such as text strings, dictionaries, or lists, each with its own structure and conventions. Challenge 2. The method needs to handle potential errors and exceptions during the information extraction process. Errors can occur due to invalid prompt formats, missing data, or unexpected content, requiring robust error handling mechanisms. Summary of LangChain experimental tools. Python tool. Python inputs. None. Python inputs is a class that defines the inputs for a Python tool. This class ensures that the inputs provided to a Python function from a large language model (LLM) are structured correctly. This class serves as a bridge between the LLM and the Python function, making it easier to integrate Python code into LLM applications. Component 1. Function name. The name of the function to be called. The function name is used to specify the particular Python function that the LLM intends to execute. For instance, if the LLM wants to call the function calculate sum, the function name will be set to calculate sum. This name should match the actual name of the Python function that is defined and available to be executed. Arguments: a dictionary of arguments to be passed to the function. This component defines a dictionary where each key corresponds to a parameter of the Python function and its corresponding value is the argument that should be passed to that parameter. The arguments are passed to the function in the order defined by the function's definition. For example, if a function has parameters a and b, and the LLM intends to pass the value 5 to a and 10 to b, the arguments dictionary would be a5, b10. Quarks: a dictionary of keyword arguments to be passed to the function. This component defines a dictionary where each key represents the name of a keyword argument for the Python function, and its corresponding value is the value that should be passed to that argument. Keyword arguments provide a way to pass arguments to the function out of order and are identified by their names. For example, a function might have a keyword argument named operation, and the LLM might choose to pass the value addition to this argument. The Quarks dictionary would then be operation addition. Python inputs is used to define the inputs for a Python tool, which is a function that can be called from a LLM chain. The Python tool is encapsulated within an LLM chain. This chain consists of multiple components, including the LLM, the Python tool, and possibly other elements like a prompt template. The Python inputs class acts as an intermediary between the LLM and the Python tool, ensuring that the LLM's instructions and data are properly translated into the inputs required by the Python function. Python inputs allows the LLM to provide the necessary arguments and keyword arguments to the Python function. The LLM's role is to generate instructions and provide the necessary information to the Python function. These instructions and information are encapsulated in the Python inputs object. The Python inputs class then translates the LLM's input into a format that the Python function can understand, allowing the function to be executed correctly. Allows for flexible and dynamic interaction between LLMs and Python code. This class provides a flexible interface that enables the integration of Python functions into LLM applications. The inputs to the Python function can be dynamically generated by the LLM, allowing for a variety of different use cases and scenarios. For instance, the LLM could provide different arguments or keyword arguments based on the context of a conversation or the specific task at hand. Simplifies the process of defining inputs for Python tools. Python inputs streamlines the process of defining inputs for Python tools, making it easier to connect LLMs with Python functions. The class ensures that the input format is correct and consistent, reducing the complexity of managing inputs for Python tools and allowing developers to focus on the core functionality of the Python function, ensuring the correct format of inputs provided by the LLM. This challenge arises from the need to make sure that the input provided by the LLM aligns with the requirements of the Python function. The LLM might not always generate inputs in the exact format expected by the function. For instance, the LLM could provide a list of arguments when the function expects a dictionary, or it could provide a string instead of an integer, handling potential errors that may occur during the execution of the Python function. The challenge here is to ensure that the Python function executes correctly and to manage potential errors that could occur during execution. The execution of the Python function might fail if there are issues with the input provided by the LLM or with the function itself. Handling these errors gracefully, such as logging the errors or returning informative messages to the LLM, is crucial for the overall functionality of the system. Langchain experimental text splitter. Definition. Langchain experimental text splitter is a module within the LangChain library that provides a structured way to split text into smaller, more manageable chunks for efficient processing by large language models (LLMs). This enables the handling of large input documents that exceed the typical token limits of LLMs. For instance, imagine you have a lengthy research paper that you want to summarize using a large language model. The paper might be too large to be processed by the model in one go. The LangChain experimental text splitter can break down the paper into smaller, more manageable chunks, each of which can be processed individually by the model. The results from each chunk can then be combined to create a summary of the entire paper. Components. Component 1. Text splitter class. This class is the core component responsible for performing the splitting of text based on predefined criteria. This is the foundation of the text splitting process and offers a flexible framework for customizing the splitting behavior. For example, you can define rules for how to split text based on specific characters or patterns. Component 2. Character text splitter. A specific subtype of text splitter that splits text into chunks of a specified maximum character length. This type of splitter is ideal for situations where the size of text chunks needs to be controlled based on character count. A common example is splitting a large text file into chunks that are limited to a specific character length, ensuring compatibility with APIs that have character limits. Component 3. Token text splitter. Another subtype of text splitter that splits text into chunks based on the number of tokens, considering the tokenization rules of a given LLM. This splitter is tailored to the specific tokenization rules of a particular large language model. Different models may have different tokenization rules, so this splitter ensures compatibility by dividing text based on these rules. This approach is useful when you need to ensure that the chunks are consistent with the model's tokenization process for optimal results. Architecture. The text splitter class is designed to be versatile and extensible. It provides a configurable framework for splitting text based on different criteria. The core text splitter class serves as a base for various specialized subtypes, each tailored to handle specific splitting scenarios. The architecture of the text splitter class allows for different splitting strategies. For example, you can choose to split text based on character length, token count, or by identifying specific patterns within the text. Role. The LangChain experimental text splitter plays a crucial role in enabling the effective processing of large text inputs by LLMs by breaking down large documents into smaller, more digestible chunks. It facilitates the efficient utilization of LLMs for tasks such as summarization, question answering, and document analysis. The LangChain experimental text splitter is an indispensable tool for anyone working with large language models. By breaking down large text inputs into smaller, more manageable chunks, it enables the efficient use of LLMs for a variety of natural language processing tasks. This makes the process of working with LLMs more efficient and effective, particularly when dealing with large amounts of text. Advantages. Advantage 1. Enhanced LLM performance by handling large text inputs efficiently. The ability to handle large inputs without exceeding the token limits of LLMs improves the overall performance of the models. For example, imagine you are analyzing a massive dataset of customer reviews. The LangChain experimental text splitter can break down this dataset into manageable chunks, allowing the LLM to process the data more efficiently and provide accurate insights. Advantage 2. Improved processing speed by breaking down large tasks into smaller, manageable chunks. By dividing large tasks into smaller, more digestible chunks, the processing speed is significantly enhanced. This is particularly beneficial when working with large text files, where the processing time can be reduced significantly. Imagine you are running an LLM based chat assistant. By splitting the user's input into smaller chunks, the assistant can process the conversation more quickly and respond in a timely manner. Advantage 3. Flexible configuration options allow for tailored text splitting based on specific requirements. The LangChain experimental text splitter provides a range of configuration options, enabling you to customize the splitting process to meet your specific needs. You can define the maximum chunk size, specify splitting criteria, and adjust other parameters to achieve the desired results. For example, you can configure the splitter to prioritize splitting text based on paragraphs, sentences, or specific keywords. Challenges. Challenge 1. Maintaining the integrity of context and meaning when splitting text into separate chunks. One of the key challenges is ensuring that the context and meaning of the original text are preserved when splitting it into chunks. For example, if a paragraph is split in the middle of a sentence, the meaning may be lost. The LangChain experimental text splitter tries to address this by providing mechanisms to maintain context across chunks. Challenge 2. Handling complex text structures, such as nested lists or code blocks. During the splitting process, complex text structures, such as nested lists or code blocks, pose challenges for text splitters. Maintaining the integrity of these structures while splitting can be tricky. The LangChain experimental text splitter attempts to address this by providing options for handling specific text elements, such as code blocks, while splitting. Challenge 3. Striking a balance between chunk size and the need for sufficient context within each chunk. A crucial aspect is finding the right balance between the size of the chunks and the need for sufficient context within each chunk. Too large chunks can be difficult for LLMs to process, while too small chunks can lead to loss of context. The LangChain experimental text splitter provides mechanisms to help find this balance, allowing you to specify the chunk size and set other parameters that influence context retention. LangChain experimental tabular synthetic data. Definition. Detailed definition of the LangChain experimental tabular synthetic data module. The LangChain experimental tabular synthetic data module is a powerful tool for generating synthetic tabular data. It enables developers and data scientists to create artificial datasets that mimic the characteristics of real-world data. This synthetic data can be used for a variety of purposes, including testing, debugging, privacy-preserving data sharing, and generating training data for machine learning models. Components. Component 1. A function that generates synthetic tabular data based on real data. This component leverages real data as input to create synthetic data that maintains the statistical properties and relationships present in the original data. It can be used to generate realistic datasets for testing data pipelines, ensuring that they are robust and handle real-world data scenarios effectively. Component 2. A function that generates synthetic tabular data based on a schema. This component provides the flexibility to generate synthetic data based on a predefined schema. It allows users to define the structure and data types of the synthetic dataset, ensuring that it conforms to specific requirements and data models. This is useful for generating training data for machine learning models where specific features and data distributions are needed. Architecture. Description of the architecture supporting the LangChain experimental tabular synthetic data module. The architecture of the LangChain experimental tabular synthetic data module is comprised of two primary components. 1. Tabular synthetic data generator responsible for creating synthetic data based on real data. This component analyzes the statistical properties and relationships within the real data and uses them to generate synthetic data that mimics the original distribution and patterns. This component is ideal for creating synthetic datasets that are realistic and representative of real-world scenarios. 2. Schema-based synthetic data generator responsible for creating synthetic data based on a schema. This component allows users to define the structure and data types of the synthetic dataset using a predefined schema. It generates data that adheres to the specified schema, ensuring compatibility with specific applications and systems. This component is particularly useful for generating training data for machine learning models where specific feature types and data distributions are needed. Role. Explanation of the LangChain experimental tabular synthetic data module's role in the system. The LangChain experimental tabular synthetic data module plays a crucial role in providing functionality for generating synthetic tabular data. This synthetic data can be used for a variety of purposes, such as 1. Testing and debugging data pipelines. The module enables the creation of realistic synthetic datasets for testing and debugging data pipelines. This helps ensure that data pipelines are robust, handle real-world data scenarios effectively, and identify potential issues before deploying them in production. 2. Privacy-preserving data sharing. The module provides a mechanism for generating synthetic datasets that preserve the statistical properties of real data while protecting sensitive information. This enables the sharing of data for research, collaboration, or analysis without compromising privacy. 3. Generating training data for machine learning models. The module offers the flexibility to generate synthetic datasets that meet specific requirements for training machine learning models. This allows developers and data scientists to create datasets with desired features, distributions, and data types, ensuring that the models trained on these datasets are effective and generalize well to real-world data. Advantages. Ability to generate realistic synthetic data that can be used for a variety of purposes. The module's ability to generate realistic synthetic data is a significant advantage. This synthetic data can be used for a variety of purposes, including testing and debugging data pipelines, privacy-preserving data sharing, and generating training data for machine learning models. It allows developers and data scientists to work with realistic datasets that are representative of real-world scenarios, leading to better results and insights. Flexibility to generate synthetic data based on either real data or a schema. The flexibility to generate synthetic data based on either real data or a schema is another important advantage. This allows users to tailor the synthetic data generation process to their specific needs. Using real data enables the creation of synthetic datasets that are statistically representative of real-world data, while using a schema allows for greater control over the structure and data types of the synthetic data. Challenges. Ensuring that the generated data is representative of the real data. One challenge in generating synthetic data is ensuring that it accurately represents the characteristics and patterns of the real data. The module aims to address this challenge by using various data generation techniques that capture the statistical properties and relationships within the real data. However, achieving complete representativeness can be complex. especially when dealing with complex data distributions or rare events. Ensuring that the generated data is privacy preserving. Another crucial challenge is ensuring that the generated data is privacy preserving. The module aims to protect sensitive information by generating synthetic data that does not contain identifiable details. However, it is important to carefully consider privacy concerns and implement appropriate anonymization techniques to avoid unintended disclosure of sensitive information. Generating data that meets specific requirements. Generating data that meets specific requirements is an ongoing challenge. This might involve generating data with specific distributions, correlations, or data types. The module provides some capabilities for specifying these requirements. But addressing complex or highly specific requirements might require further customization or development. langchainexperimental.sql Vector SQL.getResult from SQLDB. Definition. Detailed definition of the langchain experimental SQL vector SQL getResult from SQLDB function. This function utilizes a combination of vector and SQL databases to retrieve information from a SQL database based on vector embeddings. Components. Component 1. A vector database used to store and query vector embeddings. A vector database is a specialized database designed to store and query vector embeddings. Vector embeddings are numerical representations of data, often used to capture semantic relationships between data points. For example, a vector database could be used to store embeddings of product descriptions, allowing users to search for similar products based on their descriptions. Component 2. A SQL database used to store and query structured data. A SQL structured query language database is a traditional database system used to store and manage structured data. This data is organized in tables with rows and columns, and SQL queries are used to retrieve and manipulate the data. For example, a SQL database could be used to store customer information, such as names, addresses, and purchase history. Architecture. Description of the architecture supporting the langchain experimental SQL vector SQL getResult from SQLDB function. The architecture consists of a vector database and a SQL database. The architecture combines a vector database and a SQL database to enable efficient data retrieval. The vector database stores vector embeddings that represent the semantic meaning of data, while the SQL database stores structured data. The function leverages both databases to retrieve relevant results based on the query's semantic meaning. Role. Explanation of the langchain experimental SQL vector SQL getResult from SQLDB function S role in the system. This function helps to retrieve results from a SQL database based on a vector database. The function acts as a bridge between the vector database and the SQL database, enabling users to retrieve data from the SQL database based on semantic similarity search in the vector database. This approach allows for more flexible and accurate data retrieval, considering the meaning of the query rather than just exact keyword matches. Advantages. It allows to leverage the power of both vector and SQL databases to answer complex queries. The function combines the strengths of both vector and SQL databases to provide a powerful solution. For complex data retrieval, vector databases allow for semantic similarity search, while SQL databases excel at structured data querying. This combination enables users to formulate queries that consider both the meaning and the structure of the data. It enhances the efficiency and accuracy of data retrieval by combining vector and SQL databases. The function improves the efficiency and accuracy of data retrieval. The semantic search capabilities of vector databases allow for more relevant results, while the structured querying capabilities of SQL databases ensure that the retrieved data is consistent and well-organized. Challenges. Ensuring the consistency between vector and SQL data can be challenging. Maintaining consistency between the vector database and the SQL database can be a challenge, especially when the data in the two systems is updated independently. Any discrepancies between the vector embeddings and the structured data can lead to inaccurate retrieval results. Managing the vector and SQL databases separately can increase complexity. Managing two separate databases, a vector database and a SQL database, can add complexity to the system. This includes tasks such as data synchronization, security management, and performance optimization. Langchain experimental, text splitter, combined sentences. A detailed explanation of the functionality and usage of the combined sentences method within a LangChain framework. This method allows combining sentences into larger chunks, providing a way to control the size of documents used for processing. This method is particularly useful when working with large text documents. By combining sentences into larger chunks, this method helps to reduce the number of documents that need to be processed, which can improve efficiency. This method also helps to ensure that the meaning of the original text is preserved. Component 1. This function enables the creation of larger text chunks by joining sentences. For example, if a document contains multiple sentences, this function can combine these sentences into a single, larger chunk. This can be helpful for tasks such as summarization or question answering, where it is necessary to process large amounts of text. Component 2. This method allows for customized control over the size of documents used for processing. This control allows users to specify the desired size of the chunks that are created. This can be useful for tasks such as summarization or question answering, where it is necessary to process large amounts of text. This method allows users to specify the desired size of the chunks that are created. This method is an integral part of the text splitting process within LangChain, enhancing its ability to handle large text documents effectively. This method works by taking a large text document as input and splitting it into smaller chunks. These chunks can then be processed individually, which can improve efficiency and reduce memory usage. This method plays a crucial role in LangChain, facilitating the effective handling of large documents by dividing them into manageable chunks, while maintaining semantic coherence. This method is used to break down large documents into smaller, more manageable pieces. This process helps to ensure that the meaning of the original text is preserved, and it allows for more efficient processing of the text. This method allows for efficient document processing by splitting them into smaller, manageable chunks. This method helps to reduce the number of documents that need to be processed, which can improve efficiency. The ability to process documents more efficiently can be particularly beneficial for tasks such as summarization or question answering, where it is necessary to process large amounts of text. This method enables the preservation of semantic context by combining sentences that are logically connected. This method helps to ensure that the meaning of the original text is preserved. It does this by combining sentences that are logically connected, which helps to prevent the loss of meaning that can occur when sentences are split into smaller chunks. This method may not always be suitable for all types of text, particularly those with complex sentence structures or frequent transitions between topics. For example, If a document contains a lot of technical jargon or if it is written in a very formal style, this method may not be able to effectively combine sentences into larger chunks. This method may not be able to handle all types of formatting or text styles effectively. For example, if a document contains a lot of formatting, such as bold text or italics, this method may not be able to effectively combine sentences into larger chunks. Components. A detailed breakdown of the langchain experimental .tot library, encompassing its definition, components, architecture, role, advantages, and challenges. A Python library that extends LangChain's capabilities to facilitate the development of generative agents. LangChain is a powerful library for building applications powered by large language models. langchainexperimental.tot builds upon this foundation by providing specialized tools in structures specifically tailored for the creation of generative agents. These agents are capable of interacting with the world, learning from experience, and autonomously carrying out tasks based on user instructions. Agent, a core component of the framework, responsible for orchestrating the interaction of various tools and models to fulfill tasks. The agent acts as the central brain of the generative system. It receives user requests or goals and determines the appropriate sequence of actions involving various tools and models to achieve the desired outcome. For example, if a user requests to book a flight, the agent might first use a tool to retrieve flight information, then employ a language model to summarize the options, and finally utilize another tool to make the booking. Tool provides functionality that enables the agent to interact with the external world or access relevant data. Tools serve as the agent's hands and eyes, allowing it to engage with external systems or retrieve information needed to complete tasks. Examples of tools include an application programming interface API for accessing weather data, a web scraping tool for retrieving information from websites, or a calculator for performing mathematical operations. Memory stores information about the agent's history and context to maintain continuity in its interactions. Memory is essential for enabling the agent to learn and adapt over time. It allows the agent to retain information from previous interactions, enabling it to understand the context of current requests and make more informed decisions. For instance, an agent assisting a user with planning a trip would store information about the user's preferences, previously searched destinations, and any bookings made, thus providing a personalized experience. The framework utilizes LangChain's foundation, leveraging its existing components and functionalities to provide a structured approach to building generative agents. langchainexperimental.tot leverages LangChain's core features and components, such as its chain system and model integration capabilities, to provide a robust and well-organized framework for building generative agents. This architecture enables developers to quickly assemble and deploy agents by utilizing pre-built components and standardized interfaces. The langchainexperimental.tot library provides developers with a set of tools and utilities specifically designed for building generative agents. The library aims to simplify the process of creating these complex systems by providing readily available components and a well-defined framework. It empowers developers to build sophisticated agents capable of engaging in open-ended conversations, performing tasks in the real world, and adapting to changing contexts. Simplified agent development streamlines the process of creating agents by providing readily available components and a structured framework. langchainexperimental.tot offers pre-built components, including agents, tools, and memory systems, which can be easily assembled to create complex generative agents. This modular approach significantly reduces the development time and effort required to build agents, allowing developers to focus on the unique aspects of their applications. Enhanced capabilities leverages LangChain's existing features and tools to extend the capabilities of generative agents. By building upon the foundation of LangChain, langchainexperimental benefits from its vast library of features and integrations. This includes access to a wide range of language models, diverse tools for interaction with external systems, and powerful chain mechanisms for orchestrating complex workflows. These capabilities enable developers to create agents with advanced functionalities, such as natural language understanding, code generation, and creative content creation. Limited documentation and support due to its experimental nature. The library may have limited documentation and support compared to mature libraries. As a relatively new library, langchainexperimental may have less comprehensive documentation and community support compared to more established libraries. This can present challenges for developers who are new to the library or encounter complex issues that require assistance. Complexity. Building complex generative agents can be challenging, requiring careful consideration of agent design and integration of various components. Designing and implementing generative agents involves a number of complex considerations. Developers need to carefully choose appropriate tools and models, manage agent memory effectively, and ensure seamless integration between various components. Building sophisticated agents capable of handling complex tasks and adapting to diverse situations can require significant expertise and experience. LangChain Experimental Tools. A collection of experimental tools for enhancing language models. A collection of experimental tools designed to enhance the capabilities of language models. These tools provide additional functionalities that go beyond basic text generation and aim to improve the overall performance and applicability of language models in various domains. Component 1. Tools that provide additional functionality beyond basic text generation, such as code generation tools for generating code in various programming languages. These tools can help developers automate tasks, create prototypes, and generate code snippets for specific functions. For instance, a developer might use a code generation tool to generate a Python function for retrieving data from a specific API. Data extraction tools for extracting data from various sources, including web pages, documents, and databases. Data extraction tools can help automate the process of gathering information from different sources, saving time and effort for users. For example, a researcher might use a data extraction tool to extract specific data points from a research paper. Or a journalist might use it to collect information from multiple websites for a story. Reasoning and problem-solving tools for enhancing the reasoning and problem-solving abilities of language models. These tools aim to improve the logical thinking and decision-making capabilities of language models, enabling them to tackle complex problems and provide more accurate and insightful answers. For example, a customer service chatbot might use a reasoning and problem-solving tool to understand a customer's issue, identify the root cause, and suggest a relevant solution. Component 2. Tools for building and deploying language model applications. Agent frameworks. Tools for building agents that can interact with the world and make decisions based on their understanding. Agent frameworks provide the structure and capabilities for creating autonomous agents that can perceive their environment, gather information, and take actions based on their goals and knowledge. For example, A virtual assistant might use an agent framework to interact with various applications and services, gather information about a user's preferences, and perform tasks based on their instructions. Chatbots and conversational AI tools for building chatbots and other conversational AI applications. These tools allow developers to create interactive agents that can communicate with users through text or voice. For example, a customer support chatbot might use conversational AI tools to understand customer queries, provide helpful information, and resolve issues efficiently. Custom tools and integrations tools for integrating language models with other systems and creating custom tools. These tools facilitate the integration of language models with existing systems and allow developers to create custom tools tailored to specific needs. For instance, a company might use a custom tool to integrate a language model with their CRM system, enabling the model to analyze customer data and provide personalized recommendations. The tools are designed to be modular and extensible, allowing users to easily combine and customize them to build custom applications. This modular design allows users to pick and choose the tools they need for a specific application, providing flexibility and adaptability. The extensible nature enables users to add new tools and features as needed, ensuring that the platform remains relevant and up to date. To extend the capabilities of language models and enable the development of new and innovative applications, these tools aim to unlock new possibilities for language models, allowing developers to create more powerful and sophisticated applications that address real-world challenges and provide solutions in various domains. Flexibility allows for customization and integration with other systems. The modular design allows users to pick and choose the tools they need for a specific application, providing flexibility and adaptability. This ensures that the tools can be tailored to specific needs and integrated into existing systems seamlessly. Extensibility enables users to easily add new tools and features. The extensible nature allows users to add new tools and features as needed, ensuring that the platform remains relevant and up to date. This allows users to adapt to evolving requirements and incorporate new technologies as they become available. Enhanced capabilities provides additional functionality beyond basic text generation. These tools offer additional functionalities that go beyond basic text generation, improving the overall performance and applicability of language models in various domains. This allows developers to create more powerful and sophisticated applications that address real-world challenges and provide solutions in various domains. Experimental nature may be prone to bugs or instability. These tools are still under development and may be prone to bugs or instability. This means that users may encounter occasional errors or unexpected behavior. Limited documentation. Some tools may lack comprehensive documentation. As these tools are still under development, the documentation may not be as comprehensive as it is for mature products. This can make it challenging for users to understand how to use the tools effectively. Compatibility issues. Some tools may not be compatible with all language models. These tools are not always compatible with all language models. This can limit the choices for users and make it difficult to use the tools with specific language models. Langchainexperimental based to T-chain explained. Nan. A chain that can be used to execute a sequence of functions, passing the output of each function to the next. This allows for complex workflows to be built by chaining together different functionalities. Imagine a workflow for creating an automated blog post, where you first extract relevant data from a source, then use a language model to generate a draft post based on the extracted information, and finally, Format the generated draft into a polished blog post. This entire workflow can be implemented as a to-T chain by combining these individual functions into a chain. Component 1. A chain that can be used to execute a sequence of functions, passing the output of each function to the next. The functions in the chain can be simple, such as retrieving data from an application programming interface API, or complex, such as running a machine learning model. This allows for flexibility in creating chains that can be used to automate a variety of tasks. For example, you could create a chain to translate a document into multiple languages, or to generate summaries of different articles on a topic. Component 2. A chain that can be used to execute a sequence of functions, passing the output of each function to the next. Each function in the chain takes the output of the previous function as its input, allowing for a flow of information through the chain. This can be particularly helpful for automating tasks that involve multiple steps, such as processing a request from a user, fetching relevant data from a database, and generating a response. The architecture of the chain is defined by the order of the functions in the chain. This order determines the flow of information through the chain. For example, a chain that is designed to translate text from one language to another might have a function for detecting the source language, followed by a function for translating the text, and finally a function for formatting the translated text. This architecture allows for a structured and organized approach to implementing complex workflows. The chain can be used to automate a variety of tasks, such as generating text, translating languages, or summarizing documents. To-T chains can also be used for more complex tasks such as building a chatbot that can respond to user queries in a natural way, or creating a system that can automatically generate reports from data. Advantage 1. The chain is easy to use and can be customized to meet the needs of a variety of applications. The modularity of to-T chains allows for easy customization by adding, removing, or modifying functions within the chain. This makes to-T chains versatile and suitable for different use cases. For instance, you can adjust a chain for generating text to include a function for sentiment analysis, allowing the chain to produce text that resonates with the desired tone and style. Advantage 2. The chain is efficient and can be used to process large amounts of data. The sequential execution of functions within the chain can leverage parallel processing capabilities, allowing for efficient processing of large amounts of data. For example, a chain that processes a large dataset of customer reviews can utilize parallel processing to efficiently extract relevant information and generate summaries for each review. Challenge 1. The chain can be difficult to debug if the functions in the chain are complex or have side effects. Debugging a to-T chain with complex functions can be challenging due to the potential for unforeseen interactions between functions. This can make it difficult to isolate the root cause of errors. For instance, if a function in the chain modifies a shared data structure, it can introduce unexpected behavior in subsequent functions. Challenge 2. The chain can be slow if the functions in the chain are computationally expensive. The execution time of a to-T chain can be affected by the computational complexity of its functions. This can become a bottleneck if the functions involve intensive operations, such as processing large amounts of data or running complex algorithms. For example, a chain that involves processing images might have a function for object detection which can be computationally expensive, leading to a longer execution time for the entire chain. Langchainexperimental .tot memory to TDFS memory. A memory class for storing and retrieving information from a to TDFS database. A memory class that uses a TDFS database for storing and retrieving information. The TDFS database stores information in a structured format and provides efficient mechanisms for retrieving data based on various criteria. The langchain memory class acts as an interface to this database, allowing applications to interact with the stored information. Component 1. TDFS database. A TDFS database, which stands for Time-Oriented Temporal Data Framework System, is a specialized database system optimized for storing and querying temporal data. It excels in managing time series information, making it ideal for applications like financial analysis, sensor readings, or historical records. This database is crucial for the TDFS memory class as it provides the underlying storage mechanism for all information. Component 2. Langchain memory. This refers to the memory component within the langchain framework. It acts as the bridge between the TDFS database and the applications using the TDFS memory class. Langchain memory provides a standardized way to interact with different memory systems, including those based on TDFS databases. It handles tasks like storing and retrieving data, managing data structures, and ensuring compatibility with other langchain components. The TDFS database is used to store and retrieve information. The langchain memory class interacts with the database to access the information. The architecture relies on a layered approach. The TDFS database serves as the foundation, storing the actual information. On top of this, the langchain memory class acts as an intermediary, providing a streamlined interface for interacting with the database. This separation allows for flexibility in managing the data storage and retrieval processes, while maintaining compatibility with the langchain framework. This memory class is used to store and retrieve information from a TDFS database. The TDFS memory class is designed to provide a robust and efficient way to manage information that has a temporal dimension. It leverages the power of the TDFS database to handle large volumes of time series data effectively. This makes it ideal for applications that require storing and querying historical data, such as financial modeling, sensor data analysis, and historical research. Scalability. The TDFS memory class offers scalability, allowing it to handle large amounts of data without significant performance degradation. This scalability arises from the underlying TDFS database, which is designed for storing and querying large datasets. The database's architecture and optimized algorithms allow it to efficiently manage data growth and provide quick responses to queries, even with a large number of records. Persistence. The TDFS memory class ensures persistence by relying on the TDFS database, which stores information permanently. The database's persistence ensures that the data is not lost even when the application or system restarts. This is crucial for applications that require maintaining historical records and ensuring data integrity over extended periods. Complexity. Using the TDFS memory class can present challenges related to its complexity, due to the specialized nature of the TDFS database and the interaction with the langchain memory component. Setting up and configuring the TDFS memory class requires a deeper understanding of both technologies. This complexity might require additional effort in terms of learning the specific APIs and configurations for both TDFS databases and langchain memory. Configuration. Configuring the TDFS memory class involves setting up the connection between the langchain memory component and the TDFS database. This configuration process requires specifying details such as the database location, credentials, and data schema. The complexity of this configuration can vary depending on the specific to TDFS database used in the chosen configuration approach. This configuration aspect can be challenging for users who are not familiar with the technical details of TDFS databases. langchainexperimental prompts, checker output parser. None. A class that handles the output of a checker, such as a plagiarism checker. The checker output parser takes the output from a checker and extracts relevant information, such as the overall percentage of plagiarism. This extracted information is then used to generate a response that can be displayed to the user. The response includes information about the percentage of plagiarism, as well as a list of any specific instances of plagiarism found. For example, a plagiarism checker might take a student's essay and compare it to a vast database of online content. The checker output parser would then process this raw output, identifying sections of text that match existing content. It would then present this information to the user in an easy-to-understand format, highlighting potential plagiarism and providing information about the source of the copied content. Component 1. This component is responsible for processing the output from a checker and extracting information about plagiarism from that output. For instance, if the checker's output is a raw text file containing lines of code, the checker output parser would analyze the structure and content of that file to identify potential instances of plagiarism. Component 2. This component is responsible for generating a response that can be displayed to the user based on the information extracted from the checker's output. The response generator would take the identified instances of plagiarism and present them to the user in a clear and concise way. This could involve highlighting the plagiarized sections of text, providing links to the original sources, and offering suggestions for how to avoid plagiarism in the future. The checker output parser utilizes a pipeline approach, with each step in the pipeline being responsible for a specific task. The pipeline first involves processing the output from the checker, followed by extracting relevant information from that output, and finally generating a response based on the extracted information. This pipeline structure ensures that the output of the checker is analyzed thoroughly, and the results are presented in a way that is understandable and actionable for the user. The role of checker output parser is to provide a user-friendly way of interpreting the results of a plagiarism checker. It does this by taking the raw output from the checker and transforming it into a more digestible format that can be easily understood by the user. For example, instead of showing the user a complex and cryptic list of code, the checker output parser would analyze the output and present the findings in a user-friendly format such as a simple report with highlighted sections of potential plagiarism. The user can easily understand the results of the plagiarism check. This is especially important for users who are not familiar with the technical details of plagiarism detection. The checker output parser allows users to quickly identify potential issues and take appropriate action without needing to interpret complex technical output. The user can quickly see the percentage of plagiarism in their text, as well as any specific instances of plagiarism found. This allows users to understand the severity of the plagiarism and take appropriate action to address it. For instance, if a user sees that their text has a high percentage of plagiarism, they may want to rewrite the text or use different sources. The output from different checkers can be formatted differently, which can make it difficult to extract the relevant information consistently. For example, One plagiarism checker may provide its results in a JSON format, while another may use an XML format. The checker output parser would need to be flexible enough to handle these different formats and extract the necessary information from each. Generating a response that is both informative and concise can be challenging, especially when there is a large amount of information to convey. The checker output parser needs to strike a balance between providing all the relevant information and keeping the response concise and easy to understand. This can be a challenge when the checker output is large or complex. langchainexperimental prompts, checker output parser summary. None. A parser that is designed to process the output of the checker tool, which is a tool used to analyze the quality of prompts. Component 1. The checker tool is a valuable component that helps to assess the quality of a prompt. It uses various criteria and techniques to analyze prompts and provide feedback on their effectiveness and clarity. This feedback often includes potential issues and suggested improvements to enhance the prompt's performance. Component 2. The checker output parser is responsible for taking the output from the checker tool and organizing it into a structured format that can be easily understood and used. It processes the output from the checker tool and presents it in a way that is readily accessible for further analysis or action. The checker output parser is structured to efficiently handle the output generated by the checker tool. It receives the output, which typically takes the form of a dictionary containing two key elements: issues and suggestions. The issues key holds information about potential problems identified in the prompt, while the suggestions key provides recommendations for addressing those issues. The primary function of the checker output parser is to interpret the output from the checker tool and provide a user-friendly representation of the analysis. It extracts the information about issues and suggestions from the checker tool's output and presents it in a clear and organized format, often as a list of issues and corresponding suggestions. The checker output parser simplifies the process of interpreting the output of the checker tool. It eliminates the need for manual parsing and provides a convenient way to access the results of the prompt analysis, allowing users to quickly understand the identified issues and recommended solutions. The checker output parser provides a consistent and standardized approach to handling the output of the checker tool. This ensures that the information about issues and suggestions is presented in a uniform manner, making it easier to compare and analyze results across different prompts or analyses. While the checker tool is helpful in identifying potential issues within prompts, it is important to acknowledge that it may not always be able to identify all potential problems. The complexity of prompts and the nuances of natural language can sometimes lead to missed issues or false positives. It is also worth noting that the suggestions provided by the checker tool may not always be the most effective or optimal solutions. The tool relies on predefined rules and algorithms, which may not capture all the context and nuances of a particular prompt. It is crucial to evaluate and consider the suggestions within the context of the specific prompt and the desired outcome. langchainexperimental prompts, checker output parser. A descriptive representation of the checker output parser class and its properties. A parser that takes the output of a function and checks if it matches the expected output. This parser is particularly useful in scenarios where you need to ensure the correctness of a function's output. For instance, you might use a checker output parser to verify that a function generating SQL queries produces valid SQL code. Component 1. The checker output parser uses a checker function to check the output of a function. The checker function is responsible for comparing the actual output of the function with the expected output. It can be a custom function tailored to your specific requirements. This allows for flexible validation of the function's output based on your criteria. Component 2. The checker output parser also uses a parse function to parse the output of the checker function. The parse function processes the results from the checker function and transforms them into a format suitable for the user. This makes it easier for users to understand the validation results. For example, it can translate complex technical results into user-friendly messages or summaries. The checker output parser is a subclass of the base output parser class. This means that the checker output parser inherits the structure and functionalities from the base output parser. This inheritance promotes code reusability and avoids unnecessary duplication of code. The checker output parser is used to check the output of a function and provide feedback to the user. It acts as a quality control mechanism for functions by ensuring their output meets the expected standards. For instance, in machine learning applications, it can be used to check the validity of predictions made by models, providing feedback to users and improving the overall performance of the application. Provides a way to check the output of a function. This enables developers to ensure the quality and accuracy of the output of their functions. For instance, in a web application, a checker output parser can be used to verify that the data sent to the front end from a back-end function is accurate and consistent. Allows for customization of the checker function and parse function. This flexibility enables you to tailor the checker output parser to your specific requirements in domain. You can define custom checker functions and parse functions to handle different types of validation scenarios. For example, you can create a checker function for validating dates or a parser function for formatting output in a specific language. The checker function and parse function must be defined correctly. If these functions are not defined correctly, the checker output parser may not be able to perform its validation tasks effectively. This requires careful consideration and testing of the functions to ensure they meet the specific requirements of your application. The checker output parser can be difficult to use if the output of the function is complex. The checker function and parse function need to handle complex data structures and output formats. In such cases, it might be necessary to develop sophisticated logic to effectively validate and parse the output. Langchainexperimental thought validity. An in-depth look at a key component of LangChain's Think Search Read framework for evaluating thought quality. Thought validity is a mechanism used within LangChain's Think Search Read framework to assess the quality of thoughts generated during the reasoning process. It plays a vital role in ensuring the effectiveness and accuracy of LangChain's reasoning capabilities. It acts as a quality control mechanism, evaluating the relevance, coherence, and validity of the generated thoughts. Component 1. Thought object. This represents a structured data representation of a thought, containing not only the thought itself but also associated metadata. Metadata can include information like the source of the thought, the context in which it was generated, and any relevant timestamps. This metadata is crucial for understanding the thought's origins and its relevance within the reasoning process. Component 2. Validity function, e.g., is valid method. This is a function that evaluates the quality of a thought based on specific criteria. These criteria could include factors like consistency with the overall reasoning goal. Does the thought contribute meaningfully to solving the problem at hand? Coherence with previous thoughts. Does the thought logically follow from the preceding steps in the Reasoning process. Factual accuracy is the information contained in the thought grounded in reliable sources. For example, in a question answering task, a validity function might check if the thought's content is relevant to the question being asked and if it aligns with the expected answer type. The thought object contains the thought itself, its associated metadata, and a validity function. The validity function is applied to the thought object to assess its quality. For instance, if the thought object is a proposed answer to a question, the validity function could check if the answer is consistent with the question, if it is relevant to the context of the question, and if it is factually accurate. Thought validity acts as a gatekeeper, ensuring that only valid thoughts are used in subsequent steps of the reasoning process. It acts as a filter, discarding thoughts that do not meet specific quality criteria. This helps to maintain the accuracy and coherence of the reasoning process and prevents the propagation of irrelevant or faulty information. In the context of a think, search, read workflow, thought validity is essential for ensuring that only the most relevant and accurate thoughts are used to inform the search and reading steps, leading to more effective and reliable results. Improves the accuracy and reliability of reasoning by filtering out invalid or irrelevant thoughts. Thought validity contributes to a more accurate and reliable reasoning process. This is crucial for applications where accurate and reliable results are essential, such as question answering, information extraction, and decision making. Reduces the generation of irrelevant or nonsensical thoughts by setting clear quality criteria for thoughts. Thought validity helps to minimize the generation of irrelevant or nonsensical thoughts. This leads to a more focused and efficient reasoning process, as the system is less likely to be distracted by extraneous or irrelevant information. For example, in a language model generating responses to user queries, thought validity can help to ensure that the responses are relevant, coherent, and informative, rather than being random or nonsensical. Defining effective validity functions for diverse reasoning tasks. Developing validity functions that are effective across a wide range of reasoning tasks can be challenging. Different tasks require different quality criteria, and finding a balance between generality and task-specific requirements can be difficult. For example, in a factual question answering task, a validity function would likely prioritize factual accuracy, while in a creative writing task, the emphasis might be on coherence and originality. Handling complex or nuanced thought validity assessments. Evaluating thought validity can be challenging, particularly in cases where the criteria for validity are complex or nuanced. For instance, assessing the validity of a thought that involves multiple steps of reasoning or relies on complex relationships between concepts can be difficult. The development of sophisticated validity functions that can effectively handle these complexities remains an active area of research. For example, assessing the validity of a thought that involves a chain of reasoning, where the validity of each step depends on the validity of the previous steps, can be a complex task that requires sophisticated validity functions. Langchain experimental text splitter. Definition: a text splitter within langchain that aims to break down text into smaller chunks suitable for various tasks like summarization, question answering, or embedding generation. This is useful when working with large text documents, as it allows for more efficient processing by breaking down the text into manageable units. Components. Component 1. Text splitting algorithms, including character-based, word-based, and sentence-based splitting. These algorithms allow for flexible text splitting based on specific requirements. For example, A character-based splitter can be used to split text into chunks of a fixed number of characters, while a sentence-based splitter can split text into chunks based on sentence boundaries. Component 2. Configuration options to fine-tune splitting behavior, such as chunk size, overlap, and separators. These options allow for customization of the text splitting process to meet specific needs. For example, the chunk size can be adjusted to control the size of each chunk, while the overlap option can be used to ensure that context is preserved across chunks. Architecture. LangChain provides a flexible framework for text splitting, enabling users to choose appropriate algorithms and adjust settings based on their specific use cases. This flexibility allows users to tailor the text splitting process to their specific needs, whether it be for summarization, question answering, or embedding generation. Role. It facilitates the efficient processing of large text documents by dividing them into manageable chunks. This can significantly improve processing speed, as tasks can be parallelized across smaller units. For example, when processing a large text corpus for summarization, the text splitter can be used to divide the corpus into smaller chunks, which can then be processed in parallel by multiple language models. Advantages. Improves processing speed by parallelizing tasks on smaller units. When working with large text documents, dividing them into smaller chunks allows for parallel processing, which can significantly reduce the time required to complete the task. For example, when using a language model to generate embeddings for a large corpus of text, the text splitter can be used to divide the corpus into smaller chunks, which can then be processed in parallel by multiple language models. Enhances the accuracy of language models by providing context within each chunk. When working with language models, it is important to provide them with sufficient context in order to achieve accurate results. Text splitters can help to ensure that each chunk of text contains enough context for the language model to understand the meaning of the text. For example, when using a language model for question answering, the text splitter can be used to divide the text into chunks that are small enough for the language model to process efficiently, while also containing enough context to allow the language model to answer the question accurately. Challenges. Maintaining coherence across chunks, especially when dealing with complex narratives or long texts. When dividing text into smaller chunks, it is important to ensure that the resulting chunks are coherent and maintain the overall meaning of the text. This can be a challenge when dealing with complex narratives or long texts, as the boundaries between chunks may not always be clear. For example, when splitting a novel into chunks, it is important to ensure that the resulting chunks do not disrupt the flow of the narrative. Finding optimal splitting parameters that balance chunk size and context preservation. When using a text splitter, it is important to find the right balance between chunk size and context preservation. Smaller chunks can improve processing speed, but may result in a loss of context. Larger chunks can preserve context, but may be more difficult to process efficiently. The optimal splitting parameters will depend on the specific task and the characteristics of a text being processed. For example, when using a text splitter for summarization, the chunk size should be small enough to allow for efficient processing, but also large enough to provide sufficient context for the language model to generate a meaningful summary. Summary of LangChain experimental tools. Python tool. Python*REPL tool. NaN. A Python read eval print loop tool that facilitates the execution of Python code within a context of a LangChain chain, employing the Python*REPL class. Component 1. Python *REPL class, which furnishes the fundamental functionality for executing Python code within the LangChain environment. The Python *REPL class provides the ability to evaluate Python code, offering features like variable assignment and the invocation of built-in functions. Component 2. LangChain, which orchestrates the flow of execution, supplying the context and essential information to the Python *REPL class. The LangChain acts as a manager, guiding the execution of the Python code within the Python *REPL class, ensuring proper communication and data flow between them. The tool leverages the Python *REPL class to interpret and execute Python code within a LangChain chain. The tool acts as a bridge between the LangChain chain and the Python *REPL class, enabling the execution of Python code within the context of a LangChain chain. Provides a mechanism to execute Python code within a LangChain chain, allowing for dynamic code execution and manipulation of data during the chain execution process. The tool enables the execution of arbitrary Python code within a LangChain chain, offering a flexible approach to data manipulation and dynamic task execution. For example, you can use this tool to perform calculations, process data, or interact with external APIs. Enables the execution of Python code within a LangChain chain, extending the capabilities of LangChain with dynamic code execution. The tool extends the functionality of LangChain by allowing the execution of Python code within the chain, enabling more complex and dynamic operations. This allows for custom logic and data processing within a LangChain chain. Provides a controlled environment for executing Python code, mitigating security risks associated with arbitrary code execution. The tool creates a safe space for executing Python code by limiting code that can be executed, minimizing security vulnerabilities. This controlled environment protects the LangChain chain from potential malicious code or unintended consequences. Potential for code execution errors and unexpected behavior, requiring careful error handling and code validation. This means that you need to be careful about the code you execute with this tool to avoid errors or unexpected behavior. Limited functionality compared to a full-fledged Python interpreter, potentially requiring additional tools or libraries for complex operations. The tool has limited functionality compared to a full-fledged Python interpreter, so you may need to use additional tools or libraries for more complex operations. For instance, accessing specific libraries or handling complex data structures might necessitate the integration of external tools. langchainexperimental. Prompts, checker output parser summarization. None. This class, checker output parser, is a fundamental component within the prompt framework. Its primary responsibility is to take the output generated by a checker and transform it into a structure that can be effectively utilized by the prompt. Component 1. This component encapsulates the parseChecker output method. This method acts as a bridge, taking the output from the checker and converting it into a structured list of tuples. This transformation ensures that the checker output is presented in a format that is easily digestible and processable by the prompt. For example, if a checker output contains a list of errors, this method can convert it into a list of tuples, where each tuple represents an error, containing details like the error type, its location in the code, and a brief explanation. Component 2. This component houses the getCheckerOutputFormat method. The role of this method is to define and return a string that represents the expected format of output generated by the checker. This expectation is crucial for ensuring that the pass checker output method can successfully process the checker's output. For instance, if the checker is expected to output a JSON object containing a list of errors, this method would return a string describing this JSON structure, including the keys and data types involved. The checker output parser achieves its purpose by meticulously analyzing the output from the checker and converting it into a standardized format that is readily consumable by the toad prompt. This process involves breaking down the checker's output into meaningful components and representing them in a structured manner. For instance, if the checker's output is a plain text string containing a list of issues, the checker output parser would parse this string and organize it into a list of tuples, with each tuple representing an individual issue, encompassing details like the error message, its location within the code, and a brief description of the problem. The checker output parser plays a critical role within the toad prompt framework. Its primary function is to act as a translator between the checker and the toad prompt. By providing a standardized format for the checker's output, the checker output parser allows the toad prompt to process the checker's feedback effectively and deliver accurate and meaningful insights to the user. This standardized format ensures that the toad prompt can readily interpret the checker's output, regardless of the specific checker being used, enabling consistent and reliable feedback delivery. This class significantly simplifies the use of checker output within the toad prompt. It provides a standardized approach to parsing checker output, eliminating the need to handle each checker's output format individually. This standardization enables greater consistency and reduces the complexity of integrating different checkers into the toad prompt framework. Imagine a scenario where you have multiple checkers, each with its own unique output format. Instead of writing custom parsing logic for each checker, this class provides a unified approach to parsing the output, allowing you to easily integrate and utilize the results of different checkers within the toad prompt. The checker output parser enhances the flexibility of the toad prompt. By accepting output from various types of checkers, it allows for a more adaptable and versatile system. This adaptability is particularly valuable in situations where you need to utilize different checkers based on specific tasks or contexts. For instance, you might have a checker for code style analysis, another for security vulnerabilities, and a third for code complexity. The checker output parser can handle the output from all these checkers, providing a unified interface for processing and presenting the results within the toad prompt. Managing and adapting to diverse checker output formats can pose a significant challenge. The format of the output can vary greatly depending on the specific checker used. Different checkers may employ different data structures, encodings, and conventions for representing their results. For instance, one checker might output a plain text string containing a list of errors, while another might generate a JSON object with detailed error information, and yet another might produce an XML document. Handling these varying formats requires a flexible and robust parsing mechanism capable of interpreting and extracting meaningful information from each format. Ensuring that the parsed checker output is accurate and complete presents another challenge. The checker's output may contain errors, inconsistencies, or ambiguities that can lead to inaccurate or incomplete parsing. The checker output parser needs to be robust enough to detect and handle such issues, ensuring that the parsed output reflects the original checker's feedback accurately. For example, the checker might output a JSON object containing an incomplete error message or a missing error code, or the plain text string output might contain formatting issues. The checker output parser needs to address these challenges by providing mechanisms for handling missing or incomplete data and identifying and resolving inconsistencies in the checker's output. Langchain-experimental tote-based T-chain. Langchain-experimental tote is an experimental feature in LangChain that provides a way to access information from external tools and services without the need for a separate application programming interface call. This feature allows users to directly integrate external tools and services into the LangChain's large language model chain, simplifying the workflow and enhancing its capabilities. An experimental feature in LangChain that provides a way to access external tools and services without requiring a separate application programming interface call. This feature allows users to directly integrate external tools and services into the LangChain's large language model chain, simplifying the workflow and enhancing its capabilities. Component 1. Tools refer to external applications or programs that perform specific tasks, such as weather forecasting, translation, or data analysis. These tools can be integrated into LangChain using langchainexperimental tote. Component 2. Services encompass platforms or systems that offer specific functionalities, such as email services, payment processing, or cloud storage. These services can be integrated into LangChain using langchainexperimental tote. Langchainexperimental tote integrates external tools and services directly into the LangChain's large language model chain, enabling users to seamlessly access and utilize these external resources without the need for separate application programming interface calls. This allows for a streamlined workflow and enhanced functionality by leveraging the capabilities of external tools and services. Langchainexperimental tote provides a way to seamlessly integrate external tools and services into the LangChain workflow for enhanced capabilities. It eliminates the need for separate application programming interface calls and simplifies the integration process. By enabling direct access to external resources, Langchainexperimental tote empowers users to leverage the power of external tools and services within their LangChain applications, reduces the need for separate application programming interface calls. This streamlines the workflow and simplifies integration with external tools and services by eliminating the need for separate application programming interface calls. Simplifies the integration of external services. Langchainexperimental tote provides a streamlined approach to integrate external services, eliminating the need for complex configurations and custom code. This enables users to easily integrate external services into their LangChain applications. Limited availability and may not be compatible with all tools and services. The availability and compatibility of external tools and services with Langchainexperimental tote might be limited. Not all tools and services may be supported, requiring users to consider alternatives or potentially develop custom integrations. Potential security concerns when integrating with external services. Integrating with external services could pose security risks, particularly if the services are not properly vetted or have vulnerabilities. Users should ensure that they integrate with trusted services and implement appropriate security measures to mitigate potential risks. Advantage 1. Access to advanced and innovative features. These utilities offer access to a wide range of advanced features that are not available in the core LangChain framework. This allows developers to experiment with cutting-edge techniques and explore new possibilities in language processing. Advantage 2. Exploring new possibilities in natural language processing. The utilities enable developers to experiment with various techniques and explore the potential of LangChain beyond traditional applications. This can lead to innovative solutions and new use cases for language models. Advantage 3. Experimenting with cutting-edge research and development. The utilities provide a platform for testing and implementing research ideas from the field of natural language processing. This allows developers to be at the forefront of advancements in the field and contribute to the development of new tools and techniques. Challenges. Challenge 1. Potential for instability and lack of maturity in some utilities. As the utilities are experimental, they may be subject to instability and lack of maturity. This means that certain functionalities may not be fully developed or may have bugs. Challenge 2. Limited documentation and support for experimental features. Experimental features may not have extensive documentation or dedicated support channels. This can make it challenging for developers to understand and use the utilities effectively. Challenge 3. Potential for breaking changes or deprecation of experimental utilities. Experimental utilities are subject to change or deprecation as the field evolves. This means that code built on experimental features may become outdated or incompatible with future versions of LangChain. Advantages. Improves reasoning and decision-making within language models. By explicitly representing thoughts and their supporting evidence, the thought class allows language models to engage in more reasoned and systematic thinking, leading to improved decision-making and problem-solving capabilities. For example, when faced with a complex question, the LM can use the thought class to break down the question into smaller parts, analyze each part individually, and then combine the results to form a well-reasoned answer. Enables tracking and referencing thought processes for explainability and debugging. The ability to capture and track thoughts within a language model's reasoning process is crucial for explainability and debugging. By providing a record of the LM's thought process, developers can understand how the LM arrived at its conclusions and identify any potential errors or biases. This transparency helps build trust in AI systems and enables more effective troubleshooting. Facilitates the creation of more sophisticated and nuanced language models. By providing a structured representation of thought, the thought class enables the development of more sophisticated and nuanced language models capable of performing complex reasoning tasks. For example, by integrating the thought class into a dialogue system, developers can create a more engaging and informative conversational AI that can follow complex lines of reasoning and provide well-supported answers to user queries. Challenges. Defining a standardized approach for representing thoughts remains a challenge. The concept of thought is inherently complex and subjective, making it challenging to define a universal representation that captures the full range of human cognitive processes. Different LMs might require different approaches to representing and managing thought processes, necessitating flexibility in the design of the thought class. Efficiently managing and retrieving thought context and evidence can be computationally demanding. The thought class relies on capturing and maintaining context and evidence, which can require significant computational resources, especially when dealing with large amounts of data. Efficient algorithms and data structures are needed to manage and retrieve this information without impacting performance. Handling the complexity of reasoning and decision-making within a dynamic context requires further research and development. Reasoning and decision-making within a dynamic context is a complex problem that requires further research and development. The thought class provides a framework for representing thought processes, but additional research is needed to develop robust and effective algorithms for managing the complexity of reasoning in real-world scenarios. For example, The ability to handle uncertainty, conflicting evidence, and changing context is crucial for building truly intelligent AI systems. Langchain experimental video captioning. Definition. This tool provides a way to automatically generate captions for video content by leveraging OpenAI's application programming interface API to process individual frames extracted from the video file. The API analyzes these frames and produces corresponding text descriptions, effectively creating captions for the video. Components. Component 1. This component is responsible for extracting individual frames from the input video file. These extracted frames serve as visual representations of the video content, providing snapshots that the OpenAI API can then process to generate captions. Component 2. This component utilizes OpenAI's application programming interface API to analyze the extracted video frames and generate text captions. The API, powered by advanced AI algorithms, interprets the visual information in each frame and translates it into meaningful text descriptions, ultimately forming the captions for the video. Architecture. This tool functions as a pipeline, taking a video as input and processing it through a series of stages to generate captions. First, the video frame extractor component extracts individual frames from the video. These frames are then passed to the OpenAI API component, which analyzes them and generates text captions. The final output is the set of captions corresponding to the video content. Role. This tool aims to simplify the process of adding captions to video content, making it easier and more efficient for content creators. By automating the caption generation process, it allows content creators to focus on creating compelling content while ensuring their videos are accessible to a wider audience. Advantages. Adding captions to video content makes it accessible to individuals with hearing impairments. Captions provide a textual representation of the audio content, enabling viewers with hearing loss to understand the video's message. This accessibility feature is crucial for promoting inclusivity and ensuring that video content reaches a wider audience. Captions enhance viewer engagement by providing a more immersive experience. The text overlay on the video screen allows viewers to follow the narrative while also providing context to the visual content. This multi-sensory approach can lead to better understanding and a more enjoyable viewing experience. For example, in a video tutorial, captions can help viewer follow the steps while also providing a transcript of the spoken instructions. Challenges. OpenAI's application programming interface API has limitations on the number of frames that can be processed at once. This limitation can present challenges for longer videos with a high frame rate, as the API might need to process the video in multiple batches. It is important to consider this limitation when choosing the video duration and frame rate to ensure efficient processing. The accuracy of the generated captions depends on the quality of the video input and the accuracy of OpenAI's application programming interface API. Poor video quality, such as low resolution or excessive noise, can negatively impact the API's ability to accurately interpret the frames and generate accurate captions. Similarly, the API's own performance can influence the quality of the captions. For example, if the API is not trained on a wide variety of video content, it may struggle to generate accurate captions for specialized or niche videos. Langchain Experimental Text Splitter. This document details the capabilities and functionalities of the Langchain Text Splitter tool, designed to facilitate the efficient processing of large text datasets by splitting them into manageable chunks. A text splitter is a tool designed to break down large pieces of text into smaller, More manageable chunks. This is often necessary in natural language processing (NLP) tasks, where processing large blocks of text can be computationally expensive or inefficient. LangChain's text splitter class provides various strategies for splitting text, making it a valuable tool for working with large text datasets. Component 1. The text splitter class is a core component of LangChain, providing the foundation for splitting text into smaller, manageable chunks. It encapsulates the logic and functionality for various splitting strategies. Component 2. The text splitter class offers a range of methods for splitting text, including split text. This method allows splitting plain text into chunks based on various criteria such as character count, word count, or token count. Split documents. This method is designed for splitting documents represented as dictionaries with page content fields. It enables processing documents with multiple pages by splitting them into smaller chunks for efficient analysis. The text splitter class is designed to work with various text formats, including plain text and documents represented as dictionaries with page content fields. It can be used independently or integrated into larger LangChain pipelines. For instance, it can be used as a preprocessing step before feeding text into a language model for analysis or generation tasks. The text splitter plays a crucial role in enabling efficient processing of large text datasets by breaking them down into manageable chunks. This makes it easier for language models to process and understand the information, leading to improved performance and accuracy in NLP tasks. For example, in a document summarization task, the text splitter can divide a long document into smaller segments, allowing the language model to focus on each segment individually and extract key information more effectively. The text splitter provides flexibility in choosing splitting strategies based on the specific text and task requirements. This adaptability allows users to tailor the splitting process to optimize performance and accuracy for different applications. For example, when dealing with a technical document with complex terminology, splitting based on token count might be preferred to preserve the integrity of technical terms and phrases. Breaking down large texts into smaller chunks significantly improves processing speed and resource utilization. This is particularly beneficial when working with large datasets or when dealing with computationally intensive tasks, such as training large language models. For example, in a question-answering task, splitting a large corpus of text into smaller chunks can reduce the processing time required to find relevant information and generate accurate answers. One challenge with text splitter is handling potential overlaps between chunks when splitting based on character counts or tokens. This can occur when the splitting criteria result in segments that partially overlap. Addressing this challenge is crucial for maintaining the semantic coherence of the split text and preventing inconsistencies in subsequent processing steps. For example, if a sentence is split across two chunks, it's important to ensure that both chunks are properly considered during analysis to avoid losing context or misinterpreting the meaning. It's essential to ensure that the splitting process doesn't fragment important contextual information within the text. Maintaining the contextual integrity of the text is crucial for accurate and meaningful analysis. For example, splitting a text that discusses a complex topic like the history of a specific event should be done carefully to avoid severing important connections between different parts of the text. LangChain Experimental Tote Checker to T-Checker Summary. NaN. LangChain Experimental Tote Checker to T-Checker is a class designed to detect and address potential Time of truth. Tote issues within a LangChain chain. Tote issues arise when the information used by a chain becomes outdated or inaccurate due to time-sensitive factors. Component 1. Chain. This refers to the specific LangChain chain being analyzed for tote issues. It represents the sequence of components and steps that the chain executes to generate an output. Tote checker. This is the instance of the tote checker class itself, responsible for conducting the tote analysis of the chain. The tote checker class employs a chain-wary approach to tote detection. This means that it considers the internal structure and dependencies of the chain being checked. Instead of merely assessing individual components, it analyzes the chain's overall flow and potential tote issues that might arise due to the interaction of its components. The role of the tote checker class is to ensure the accuracy and reliability of results produced by LangChain chains. It plays a crucial role in identifying and mitigating potential tote issues, ensuring that the chain's outputs remain consistent with up-to-date information. For example, consider a chain that fetches news articles and then summarizes them. A tote issue might arise if the chain relies on cached information or stale articles, leading to inaccurate summaries. The tote checker can identify such problems and suggest ways to improve the chain's reliability by accessing more recent data. Helps prevent unexpected behavior by identifying potential tote issues by proactively identifying and addressing tote issues. The tote checker helps prevent situations where a chain produces unexpected or inaccurate outputs due to outdated information. This enhances the predictability and reliability of the chain's results, promotes accurate and reliable results by ensuring that the chain uses up-to-date information. The tote checker helps ensure that chains use the most current and relevant information for their operations. This is critical for applications where accuracy and timeliness are paramount. Can potentially add overhead to the chain execution process. Introducing a tote checker into a chain can sometimes increase the overall execution time. This overhead arises from the additional steps required to analyze the chain for tote issues. Requires careful consideration of the chain structure and dependencies to identify and mitigate tote issues effectively. Identifying and addressing tote issues effectively requires a thorough understanding of the chain's structure and dependencies. The tote checker needs to be configured and applied judiciously to avoid introducing unintended consequences or overly complex analysis. LangChain Experimental Utilities Summary. NaN. LangChain Experimental is a collection of experimental utilities designed to extend LangChain's capabilities and explore new functionalities. These utilities are developed and maintained by the LangChain community and are constantly evolving, introducing new features and improvements to the LangChain ecosystem. Component 1. Integrating tools into your LangChain applications is essential for interacting with the real world. Tool code allows you to seamlessly incorporate external tools into your LangChain pipelines, enriching your applications with real-time data and functionalities. For instance, you can use tool code to integrate a weather API into a chatbot to provide users with accurate weather updates. Retry tool helps you gracefully handle errors that might occur when interacting with external tools. This component ensures that your LangChain applications remain resilient and can recover from unexpected issues, thereby enhancing the reliability and robustness of your workflows. Consider a scenario where you are using a financial data API. Retry tool will ensure that the application keeps retrying to fetch data in case of temporary connection issues or API outages. Cache enables you to store and retrieve outputs from your tools, preventing redundant computations and speeding up your workflows. By caching previous results, you can significantly improve the performance of your LangChain applications, especially when dealing with computationally intensive tools. For example, in a question answering system, you could cache the results of complex queries, allowing subsequent requests for the same information to be served much faster. Component 2. SERP provides access to SERP API, a powerful web search API that enables you to extract structured data from search results pages. You can use this component to retrieve information from various search engines and platforms, including Google, Bing, and Amazon. This data can be used to augment your LangChain applications with relevant and up-to-date information. Imagine you want to create a chatbot that answers questions about current events. By using SERP to query a search engine, you can retrieve recent news articles and provide the chatbot with the latest information. Wolfram Alpha allows you to tap into Wolfram Alpha's vast knowledge base, a computational knowledge engine that provides answers to factual queries. You can use this component to retrieve information on a wide range of topics, including mathematics, science, history, and culture. This makes it ideal for building applications that require factual accuracy and comprehensive knowledge. For example, you could use Wolfram Alpha to build a chatbot that can answer complex science questions or provide historical information. OpenAI Functions bridges the gap between LangChain and OpenAI's powerful functions. This integration enables you to use OpenAI functions directly within your LangChain pipelines, expanding your application's capabilities with advanced AI functionalities. OpenAI functions, such as summarization, translation, and code generation, can significantly enhance your LangChain applications. For example, you could use OpenAI functions to integrate OpenAI's text summarization function into a chatbot to provide users with concise summaries of lengthy articles or documents. The utilities are built on top of LangChain's core components, leveraging its modularity and extensibility. This means they can be seamlessly integrated into your existing LangChain applications or used as building blocks for new and innovative workflows. The utilities are designed to be modular and reusable, promoting a flexible and extensible architecture. These utilities provide an experimental playground for extending LangChain's functionality, allowing developers to explore new integrations, workflows, and capabilities. They serve as a testing ground for novel ideas and advancements in the LangChain ecosystem, fostering innovation and pushing the boundaries of what's possible with large language models and AI. Enable experimentation with advanced integrations and features. These utilities encourage developers to explore the full potential of LangChain by providing access to cutting-edge integrations and functionalities. This allows developers to push the boundaries of what's possible with language models and AI, leading to innovative and impactful applications. Offer solutions for common challenges in LangChain development. These utilities address common challenges faced by LangChain developers, such as integrating external tools, handling errors, and improving performance. By providing solutions to these challenges, they simplify the development process and empower developers to create more robust and efficient applications. Provide a platform for building custom tools and functionalities. LangChain Experimental provides a platform for developers to build their own custom tools and functionalities, extending the core functionality of LangChain. This enables developers to tailor LangChain to their specific needs and create highly specialized applications for a wide range of use cases. Experimental nature may lead to instability or API changes. Being experimental, these utilities are constantly evolving and subject to change. This means that you might encounter occasional instability or OP changes as new features are introduced or improvements are made. May require deeper understanding of langchain internals for effective use. Some of these utilities may require a deeper understanding of langchain internals to be used effectively. This means developers may need to familiarize themselves with langchain's architecture and codebase to fully leverage the capabilities of these experimental utilities. Limited documentation and support compared to core langchain modules. The documentation and support for these experimental utilities may be limited compared to core langchain modules. This means developers may need to rely more on community forums and online resources for support and guidance. Langchain Experimental Video Captioning Model Caption Model Summary. NaN. Langchain Experimental Video Captioning Model Caption Model is an interface for models that can generate captions for videos. It is a part of the LangChain library and is used to build applications that can understand and interact with video content. Component 1. Model is the core component of the caption model, responsible for generating the captions from video content. It leverages pre-trained models that have been trained on a large dataset of videos and their corresponding captions. This allows the model to learn patterns and relationships between visual content and textual descriptions. Component 2. Preprocessor is responsible for preparing the video input for the model. This involves tasks like extracting frames from the video, resizing them, and possibly applying other transformations to optimize the input for the model. This model uses a pre-trained model to generate captions for a video. The model takes the video as input and outputs a list of captions. The captions are generated using the pre-trained model, which is fine-tuned on a large dataset of videos and captions. Caption model is used to generate captions for videos. These captions can be used for a variety of purposes, such as indexing videos, making videos more accessible, or creating summaries of video content. For instance, a video sharing platform could use caption model to automatically generate captions for user-uploaded videos, making them accessible to individuals with hearing impairments. Enables understanding and interacting with video content. Caption model empowers users to understand and interact with video content through text. It provides a textual representation of the visual information, enabling individuals with visual impairments to access video content or allowing users to quickly skim through a video to understand its key points. It provides a way to generate captions for videos. This capability is valuable for making videos more accessible to a wider audience, including those with hearing impairments. It also enables the use of video content in various applications, such as search engines, which often rely on textual descriptions for indexing and retrieval. Model performance can be affected by the quality of the video. The quality of the video input significantly impacts the accuracy and fluency of the generated captions. Poor video quality, such as blurry frames, low resolution, or excessive noise, can make it difficult for the model to accurately identify and interpret the visual content, leading to errors in the captions. Generating accurate captions can be challenging for complex videos. Videos containing fast-paced action, intricate visual details, or multiple subjects can pose challenges for the caption model. The model may struggle to keep up with the rapid changes in the visual content or accurately interpret complex scenes, leading to inaccurate or incomplete captions. LangChain Experimental Video Captioning Models, Audio Model Summary. An overview of the audio model in LangChain Experimental Video Captioning Models. Components. Component 1. Langchain model refers to a framework that enables building and utilizing language models. It simplifies the process of interacting with these powerful models, making them accessible for various applications. Component 2. Hugging Face Transformers model represents a collection of pre-trained models for natural language processing tasks, including text generation, translation, and sentiment analysis. They are readily available through the Hugging Face library, offering a robust set of tools for leveraging these models. Architecture. The audio model employs a langchain model to handle audio data. This langchain model preprocesses the audio, making it suitable for input into a Hugging Face Transformers model. This Transformers model, specialized for audio-to-text conversion, then transforms the processed audio data into textual representation. Role. The primary function of the audio model is to extract textual descriptions from audio data contained within videos. This process, commonly known as video captioning, enables understanding and summarizing the content of videos through written text. The audio model operates with efficiency and speed, quickly processing audio data to generate text. This characteristic proves beneficial in applications where swift video captioning is crucial. The audio model demonstrates high accuracy in video captioning tasks. This translates into reliable and precise textual representation of video content, making it suitable for various applications. Efficient operation of the audio model necessitates specialized hardware and software resources. This can pose a challenge for users with limited computational resources. Optimizing the audio model's performance often requires fine-tuning, which involves adjusting model parameters to suit specific video data and captioning requirements. This can be a technical task requiring expertise in model training and optimization. Langchain Experimental, Video Captioning, Models, Audio Model Summary. NaN. A class representing a model for generating captions from audio. It is a powerful tool for tasks like video captioning, audio transcription, and audio summarization. Component 1. The model utilizes a pre-trained audio model to extract features from the audio data. This means that the model has been trained on a vast dataset of audio recordings and can effectively understand and represent the information present in the audio. Component 2. These extracted features are then used by a language model to generate the captions. The language model, trained on text data, is able to understand the relationships between the features and generate coherent and grammatically correct captions. The model architecture typically consists of two main components: an audio encoder and a text decoder. The audio encoder takes the audio input and converts it into a set of features that represent the key information in the audio. The text decoder then uses these features to generate a sequence of words that form the caption. The role of this model is to provide a way to generate captions from audio data. This can be extremely useful for tasks like video captioning, where the model can automatically generate descriptions for videos based on the audio soundtrack. It can also be used for audio transcription, converting spoken audio into written text, and audio summarization, providing a concise text summary of a longer audio recording. The model can leverage the power of pre-trained audio models to extract features from audio data. This means that the model doesn't need to be trained from scratch, and can benefit from the knowledge learned from the massive datasets used to train the pre-trained models. This leads to more accurate and robust feature extraction. The model can generate captions that are more accurate and coherent than traditional methods. By combining the strengths of pre-trained audio models and language models, The model can generate captions that capture the meaning of the audio more effectively and provide more natural sounding descriptions. The accuracy of the generated captions can be affected by the quality of the audio data and training data used for the audio model. Poor quality audio or a limited training dataset can lead to inaccuracies in the extracted features and the generated captions. The model may struggle with complex audio scenarios, such as those with multiple speakers or background noise. In these cases, the model may have difficulty separating the different audio sources and accurately extracting relevant information for caption generation. Langchainexperimental, video captioning, services, audio service, audio processor. A detailed description of the audio processor. A vital component within the langchainexperimental video captioning services audio service, which plays a crucial role in transcribing audio from video files to generate video captions. An audio processor within the langchainexperimental video captioning services audio service. Component 1. Audio segmentation, acoustic feature extraction, and speech recognition. This component involves breaking down the audio into smaller segments, extracting features like pitch and energy, and then using these features to recognize the spoken words. This is similar to how speech recognition services like Google Assistant work, where the audio is broken down into smaller units to identify words. Component 2. Optional Natural Language Processing (NLP). This optional component takes the recognized text and processes it further, analyzing the meaning and context of the words to improve the accuracy of the captions. Think of this as the NLP part of a chatbot, where it understands not just the words but also the intent behind the words. The audio processor is a component within the video captioning service that's responsible for processing audio from video files. It is designed to handle a wide range of audio formats and perform the necessary processing steps to extract meaningful information. It plays a pivotal role in transcribing audio into text, which is subsequently used for generating video captions. This means that the audio processor acts as the bridge between the raw audio and the final captions that viewers see on the screen. Efficient and accurate audio processing using pre-trained models. By leveraging pre-trained models, the audio processor can handle a vast amount of audio data quickly and accurately. These models are trained on massive datasets of audio, allowing them to identify different languages, accents, and speech patterns. Provides a foundation for generating meaningful video captions. The transcribed text generated by the audio processor serves as the core input for the video captioning system, enabling the generation of accurate and relevant captions. This is critical for accessibility, allowing people with hearing impairments to understand the video content. Handling audio with noise and interference. Noise and interference can significantly impact the performance of speech recognition. The audio processor needs to be robust enough to handle various levels of noise, including background music, ambient sounds, and even electronic interference, accurately transcribing diverse accents and speech patterns. Different accents and speech patterns can present unique challenges for speech recognition. The audio processor needs to be trained on diverse datasets to handle various accents and regional dialects. Langchainexperimental video captioning services caption service caption processor. NAN. Caption processor is a class that processes video captions. This class is designed to work with video content and extract meaningful information from accompanying captions. For example, if you have a video of a product demonstration, caption processor can identify key features or benefits highlighted in the captions. providing valuable insights for analysis or marketing. Component 1. Caption service: a service that returns captions for a video. This service is responsible for retrieving the captions associated with a particular video. It interacts with external APIs or resources to obtain the transcript, ensuring that the captions are accurate and up to date. For instance, a caption service might connect to a cloud-based video hosting platform like YouTube to retrieve a transcript of a video hosted there. Caption processor: a service that processes captions to extract relevant information. This service analyzes the obtained captions, identifying keywords, phrases, and concepts that are relevant to the video content. For example, it might identify the product names, features, or actions demonstrated in a video, providing structured information for further analysis or automation. Caption processor is used to process video captions. This class operates by integrating the capabilities of the caption service and the caption processor components. It first retrieves the captions from the video using the caption service, and then passes the captions to the caption processor for analysis and extraction of relevant information. This modular approach allows for flexibility and scalability, enabling the adaptation of the caption processor to different video formats and processing needs. Caption processor plays a role in understanding video content. By extracting key information and concepts from video captions, caption processor provides a valuable tool for analyzing and understanding video content. This can be particularly useful for tasks such as content summarization, sentiment analysis, or automatic tagging and indexing of video libraries. For example, by analyzing the captions of a series of product review videos, caption processor can identify recurring themes, common strengths and weaknesses, and overall customer sentiment towards the products. Advantage 1. It can help to extract key information from video captions. This ability allows for efficient identification of important facts, figures, and details mentioned within the video captions. For example, a financial video explaining investment strategies might contain information about specific investment instruments, market trends, or key performance indicators. Caption processor can quickly extract this information, enabling users to gain a rapid understanding of the video's key insights. Advantage 2. It can be used to summarize video content. This capability allows for generating concise summaries of the video content, capturing the essence of the information conveyed through the captions. This is particularly helpful for videos that are lengthy or complex, allowing users to quickly grasp the core message and relevant points. For instance, a tutorial video on a new software feature might be lengthy and detailed. Caption processor can generate a concise summary of the key steps, functionalities, and benefits of the new feature, providing a quick overview for users who may not have time to watch the full video. Challenge 1. It may be difficult to accurately process captions that are poorly formatted or contain errors. This challenge arises due to the inherent complexity of capturing and transcribing spoken language. Errors in transcription, formatting inconsistencies, or the presence of background noise can all contribute to inaccurate captions. Handling these situations requires robust algorithms and error correction mechanisms to ensure accurate processing of the captions. For example, a caption might mistakenly transcribe there as there or introduce extraneous characters, leading to misinterpretation by the caption processor. Challenge 2. It may be challenging to extract relevant information from captions that are long and complex. The challenge lies in discerning the most important information within a large volume of text. This is particularly relevant for videos that cover a wide range of topics or are highly detailed in nature. For example, a lecture video covering a complex scientific topic might contain a large amount of information, making it difficult to identify the most important points or key takeaways. Efficient algorithms and advanced natural language processing techniques are required to effectively extract relevant information from complex and lengthy captions. Flexibility to choose and integrate various image processing libraries based on specific needs. This allows for the utilization of specialized image processing libraries tailored to specific requirements, enabling the video captioning system to adapt to diverse image manipulation scenarios. For example, if a video captioning system needs to perform complex image analysis tasks, it could leverage the advanced features of a library like OpenCV. While for basic resizing operations, a simpler library like Pillow might suffice, ensuring compatibility and smooth integration with different image processing libraries. This involves managing diverse library functionalities, data formats, and APIs, ensuring that the image processor class seamlessly integrates with the chosen image processing library, allowing for reliable and consistent image manipulation. Optimizing image processing steps for real-time video captioning scenarios. This requires balancing performance efficiency with accuracy, minimizing processing times without compromising the quality of image manipulation. For instance, in real-time captioning applications, the image processor needs to process images quickly to keep up with the video stream, while still performing necessary image manipulation tasks. Langchain experimental video captioning models. Caption model. None. Detailed definition of the variable goes here. Components. Component 1. Langchain experimental video captioning model is a class that leverages various video captioning models to generate descriptive captions for videos. For example, it can be used to automatically generate captions for a video of a cat playing with a ball of yarn, describing the cat's actions in the environment. Component 2. It takes a video as input, processes it using the chosen captioning model, and returns the generated caption. This allows users to easily add captions to their videos without having to manually transcribe them. Description of the architecture supporting the variable. The model relies on a variety of video captioning models such as model name and model name. These models can be based on different architectures, such as transformer networks or recurrent neural networks, and can be trained on different datasets, leading to variations in their performance and capabilities. It provides a unified interface to interact with these models, allowing for flexible selection and application. This means that users can easily switch between different captioning models depending on their specific needs and the characteristics of the video they are working with. Explanation of the variable's role in the system. The caption model serves as a central component in LangChain's video processing capabilities. It enables seamless integration with various video captioning models, streamlining the process of extracting textual descriptions from video content. For instance, a user could use the caption model to extract the summary of a lecture video, providing a textual representation of the key points and concepts discussed. Provides a streamlined interface to leverage various video captioning models. This simplifies the process of using different captioning models, allowing users to focus on the task at hand rather than having to learn the specific APIs of each model. Offers flexibility in choosing the most suitable model for a given task. For example, a user could choose a model that is specialized in generating captions for sports videos if they are working with a video of a basketball game. Handling large video files can be computationally demanding and require optimization techniques. This is particularly true for high-resolution videos or videos that are long in duration. Ensuring the accuracy and coherence of generated captions remains a challenge. While video captioning models have made significant progress, they are still not perfect and can sometimes produce inaccurate or incoherent captions.